Ah, there we go. Okay, we are live. Welcome to APEC. It is December 21st, 2024, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. It is December 21st. We are like 4 days out from Christmas, so it is going to be a little bit chaotic today. But again, appreciation for everyone who's joining us. So Mikolaj Baczynski is going to be presenting experimental results for a vacuum propeller. He's got a video that he's going to start us out with, and he is actually trying to log in now. He's having a little bit of technical difficulty. So he'll do Q&A after we play the video. Horst Ekhardt is here also. He's going to be discussing anti-gravity concepts on the basis of Einstein-Cartan-Evans theory. And that is actually related to torsion theory too, from what I understand. So that is really exciting. Harry Sprain is going to be doing a live demo of the Centrifugal Impulse Drive, or CID. This is an inertial propulsion device that uses magnets. It is really exciting. I've seen videos of this in the past, hoping to take a trip down there to actually spend time with them and get some footage in the next few months. And then Stephen Colbern is going to be doing an overview on some of his analysis of the St. Augustine purported UFO wreckage. So lots of good stuff. We're also going to have updates from our lab partners, and we're going to try and finish off the event with an open discussion by conference attendees. So a couple of quick updates before we get started. Today's event is broadcasting on StreamYard. We're through the Alt Propulsion YouTube channel, and actually I have broadcast, we're on YouTube, LinkedIn, Facebook, you name it. So we are live streaming and multi-streaming. It's really exciting. If you haven't subscribed, please do so now. Alt Propulsion on YouTube is probably the safest bet, right? You're going to find everything there. You can ask questions if you're watching through that channel using the live chat feature on the right-hand side of the page. We will try to ask them to our presenters depending on time constraints. Also, sometimes we flash those up on the screen, especially during the like live demo Q&A type stuff. So you can also view conference replays, details, and speaker info on our website at altpropulsion.com. Let me strongly recommend visiting our site, signing up for our mailing list there at altpropulsion.com. The reason I say that is that's where we're going to list upcoming conference presentations. So I want to get started. Let me welcome our first speaker, and it looks like Mikolaj is here, so I'm going to add him very briefly to the stage. Mikolaj, welcome, sir.
Yes, I'm confused because I thought it was on Zoom, and it's not on Zoom.
No, we are on StreamYard, but I'm glad you got your technical issues solved. You look great. You sound great. So
yeah, but I had everything prepared on Zoom and everything, so I cannot share my screen and stuff like that later on. So that's what I was thinking.
Yeah, so I have a video for you. Do you want me to put the video up?
Yes, please. But my point is that if people ask questions later on, and I'd like to explain, and I would like to share a screen, that's what's available on Zoom. You know what I mean?
Yeah. So
okay, it is what it is. Okay, let's go. Let's move on. Yeah.
and we can upload the presentation. We can put that PDF up. So that is something
we can upload. Okay, do you want me to upload it again or?
Oh yeah. If you go to slides and PDFs, present slides and PDFs.
Yes.
And then your computer. Yeah.
It's already there. Yeah.
Yeah. And you can actually do complete screen share as well. So I think we should be set. So Mikolaj, let me do this. Since we have that video queued up, there we go. Okay. And it's, for some reason, it's in my email, but okay. Well, that's fine. So I am going to put that up. I will cross my fingers.
Put it here because it's too big.
Oh, I can just play it right through my computer.
Okay, that'd be great.
Yeah, let me do that. Okay, so I'm going to share my screen. Okay.
I will Welcome to the presentation. My name is Mikolaj Baczynski, and I will be introducing the idea of building vacuum propeller, pushing against a quantum foam. I will introduce the theoretical basis that, in my view, allows for building vacuum propeller, describe 3 types of experiments to validate the idea, and analyze the test results. To see how pushing against a quantum foam could be possible, let's consider the trajectories of particle-antiparticle pairs in non-uniform magnetic field. With the strength of the magnetic field varying as shown, positive-negative pair would be pushed with a different force than the negative-positive pair because the strength of the magnetic field increases along the trajectory of the positive-negative pair and decreases along the trajectory of the negative-positive pair. Given that Fa is larger than Fb, we should expect a force acting on the magnets. The order of magnitudes of the force should be expected to correspond to Casimir force. When I was trying to formulate Ty function, I couldn't find answers to the following questions. What is v, pop-out velocity in quantum foam? Is it Planck length divided by uncertainties delta t? What is particle-antiparticle density at a given moment? As a result, I have decided to focus on experimental validation. One more thing to notice is that moving the magnets would encounter resistance, and that would allow for building the vacuum propeller. The thrust force depends on field geometry. As demonstrated here, only the y component is useful to the operation of the propeller, and the resulting force may be higher despite having lower gradient of the magnetic field, because of, in this case, if we look at the y component only, Tb is larger than Ta. Is there any supporting experimental evidence for my claims? I can think of 2. Dynamical Casimir effect and extraction of vacuum energy performed by Garret Moddel from the University of Colorado. There are 3 types of experiments that can be used to validate or falsify the idea. Beam balance, I find it least convincing. Varying the magnet configurations can account for the interaction with the Earth's magnetic field. Torsion balance, I find it more convincing. Perhaps it would allow us to quantify the effect, at least at an engineering level. However, it is very difficult to compensate for the interaction with the Earth's magnetic field. Extraction of vacuum energy gives definite proof. However, this experiment is feasible only if it's possible to 100% shield the setup from the Earth's magnetic field. Also, T is very small and may not overcome friction. Let me describe the setup for the beam balance experiments. We have a laser located roughly 5 meters away from the screen, and the magnets are attached to the beam roughly 1 meter away from the pivot point. We have 2 forces that are due to the interaction with the Earth's magnetic field. One is acting on the base magnets, and the other one is acting on the single magnet. And if the force Fe2 is smaller than the resulting thrust force, we will see positive results. There are 2 test configurations. Positive bias configuration, in which interaction with the Earth's magnetic field is more likely to result in false positive outcome, and negative bias configuration, in which interaction with the Earth's magnetic field is more likely to result in false negative outcome. Either configuration can have push-down setup, in which the expected force is acting down on the beam, or push-up setup, in which the expected force is acting up on the beam. Positive versus negative bias configuration needs to be confirmed by testing with the number of base magnets set to 1. Here are the test results. The tests were performed in 2 setups: push-down setup, which is composed of base magnets, gap and bottom magnet, and push-up setup that is composed of the top magnet, gap, and base magnets. The results we can interpret as follows. First of all, by setting the number of base magnets to 1, we can determine whether the setup is positive bias or negative bias. And by having seen the results being consistent in both cases, we can determine that both setups were negative bias configurations. Looking at the results, we would like them to be correlated between push-down setup and push-up setup. We can see the correlation in green. It's like 50-50. In yellow, we can see the results that are not correlated, however, they're positive. Again, 50-50. So it's difficult to say that it's perhaps all positive. However, we can look at the results and conclude that the results, that the force depends on the field geometry. In order to confirm my assumptions, I ran simulations using FEMM software. It provides 2D modeling, which is sufficient. It provides confirmation about the interaction of the forces. That is, if the simulation results agree with the tests that indicated the existence of the T-force, then that force could not be resulting from interaction with the quantum foam. Free software has limitations. One of them is that the rod connecting the magnets could not be simulated. It was easily overcome by defining a region over the magnets and integrating the forces over that region. The boundary was set to 250 millimeters, and push-down setup and push-up setups had to be placed at different locations. The bar magnet simulating the Earth's magnetic field had its coercivity set to 47.7 amps per meter. However, if I was to increase the coercivity of the magnet simulating the Earth's magnetic field, both setups could be placed at the same location and aligned according to the geographical latitude. Increasing the coercivity of the bar magnet simulating the Earth's magnetic field 100,000 times makes the simulation qualitatively closer to the tests, and here is why. Because only the lines closer to the beam magnets are affected, and away from the beam magnets, in both cases, the lines are unaffected. That means the beam magnets have little effect on the Earth's magnetic field miles away. Field analysis with the example of push-down setup with 2 base magnets and 8 millimeter gap shown here confirms the assumptions that I made for the beam balance test. Important things here to notice that it is not the difference between the strength of this magnet and this magnet. It is important to have these lines parallel for as long as possible, and the range variance of the magnetic field very closely resemble range A. Range B is not as efficient because it's less of the going down area. However, the main conclusion here is that basically it's all about field geometry. Let's look at the results. The force acting on the beam was obtained by integrating forces over a region of integration, and this is the region of integration, and converting those forces into 1 millimeter of delta H equals roughly 100 micronewtons. However, due to the limitations of the FEMM software, the simulation results can only be qualitatively compared with the tests. The sign of delta H is expected to follow the single base magnet results, and simulations confirm the important role of field geometry. Closer look at the results, you see the results of the single base magnets, the negative here, and the same sign for all other results in the push-down setup. For the push-up setup, the single base magnet test results are all positive, and all other tests are positive as well. We can perform dual configuration beam balance experiments and compare with the single configuration beam balance. We would expect T-force to be doubled and the influence of the Earth's magnetic field totally compensated. However, one of those configurations may exhibit positive bias. In order to confirm configuration bias, I've performed tests with the single base magnets, and I would expect the following results. For the negative bias configurations, push-down setup, I would expect H-push minus H-pull to be negative, and for the push-up setup, I would expect H-push minus H-pull to be positive. The results I got for the push-down setup are all negative, which is consistent, and for the push-up setups are mixed. That means that push-up setup is inconclusive, and there's no point of performing tests in that setup. Push-down setup, it may be worthwhile performing tests in that setup. The test results look encouraging. However, there is little correlation with the single configuration tests, and that is why the results need to be discarded. Moving on to torsion balance tests. These tests need to be performed with different starting angles, in different magnet configuration, NS, SN, SN, NS, and we can analyze the forces in 2D because the size of the balance is much smaller than the Earth's radius, and the forces that we have are twisting forces, which is magnetic moment plus the force T that we're expecting to find, and push forces, which are much smaller than the twisting forces. And if all the tests in all possible configurations are positive, we have a confirmation. There are two beam configuration options. Setup A, in which we have NS, SN on one end of the beam and the same configuration on the other end of the beam, or NS, SN configuration on one end and on the other end SN, NS configuration. In the case of setup B, we have to notice that FB2 has the same direction as the T-force, and FB1 has the same direction as the T-force. That means setup B is always false positive. In the case of setup A, if we have FB2 minus FB1 being less than 0, that results in false positive. Also, if FMD is FM1 minus FM2, FM1, FM2, if that difference is less than 0, it is also false positive. The following conditions must be met. FBD plus FMD must be greater or equal than 0. Of course, we would like it to be equal. And the T-force must be greater than 0.5 times FBD plus FMD. Let's move on to the force analysis. Looking at the forces acting on a bar magnet in the Earth's magnetic field, we can distinguish 2 points. Theta equals 0 and theta equals 180 degrees. In both cases, the torque acting on the magnet is 0. However, the value of work, meaning potential energy required to keep the magnet at a given position, we have for the theta equals 0, the 0 value of the work, and for theta equals 180 degrees, we have the maximum value of work, meaning theta equals 0 is a stable position, and theta equals 180 degrees is an unstable position. And we have to make sure that in all our tests, 180 degrees position never happens. Looking at the NS-SN test setup, and for simplicity, assuming linear analysis of the forces due to the interaction with the Earth's magnetic field, we see that they all add up to 0. The work, meaning the potential energy, is constant. However, for practical applications, we need to consider cases where these forces are not balanced. In real life, we may have two situations. Situation in which FB1 is greater than FB2, and the situation where FB1 is smaller than FB2. We can ignore FM1 and FM2 because FB1 is so much greater than FM1. Okay, so in this case, where the FB1 is greater than FB2, we would have positive bias range and negative bias range. And the opposite would be for the case where FB1 is smaller than FB2. You would have negative bias range and the positive bias range. Tests were performed based on beam balance results with 3 base magnets and 1 mm gap. We have pictures showing starting angle of less than 0, roughly about 0, and greater than 0. The tests were performed with the beta 1 of -75, -40, -5, 40, and 75 degrees. For -75 degrees, we see the beam is tilting entirely to the left. The R angle is negative. For -40 degrees, the tilt is to the left with some tilt to the right. For -5, the fairly even with the tendency of going to the left. From 40 degrees, they're pretty much even. And for 75 degrees, the tilting is mostly to the right. Tilt to the left is very small. It looks like the FB2 plus M1 is stronger than FB1 plus M2. However, we see positive results in the negative bias zone, so let's take a closer look. Having positive results in the negative bias zone would suggest that the T-force exists. However, we have to consider this situation. When you have this beta 1 angle close to 0, one set of magnets is in the very stable position and the other set of magnets is in very unstable position. That leads to oscillations. So we have to find a different way of testing. We can perform comparison tests. In those tests, we have 3 setups. NS, which is a setup that we use to calibrate the test. Setup R, where we expect the beam to turn to the right. And setup L, where we expect the beam to turn to the left. We construct those setups by moving entire magnet configurations from one end of the beam to another. The test preparations are as follows. We have to establish equilibrium point for the NS configuration, meaning beta 1 equals 0. For setup R, we place the stopper where the NS configuration starts turning to the left. And for setup L, we place the stopper where the NS configuration is starting to turn to the right. The rotation stopper must be placed so that the NS configuration does not move, yet the torsion wire is exerting minimal force against the T-force. So moving on to the results. By comparing the L and the R setup results, we ensure that the effect is not caused by FB1 plus FM2 being greater than FB2 plus FM1 or vice versa, and we are eliminating oscillations caused by 180-degree angles between the magnets and the Earth's magnetic field. If you look at the results, we have achieved 100% consistency between the L and the R setups, and most of the results are positive, and that's very encouraging. We can also perform single set configuration tests where one of the magnet configurations is replaced by a non-magnetic weight balance. In those tests, we have 2 steps. Step 1 is to determine beta 1 of 0, means the 0 angle position, and in step 2, we put a rotation stopper at beta 1 slightly higher than 0 so that the single magnet is not in the unstable position. And those tests, if you look at the results, are very encouraging. However, if the ratio of FB1 to FM1 is too high, we may not see positive results at all. However, for the number of base magnets of 2, we see that the results are positive. After performing the tests and running the simulations, my conclusions are as follows. The beam balance test, the interaction with the Earth's magnetic field is constant within the beam movements. They're less sensitive than torsion beam tests, and dual configuration tests didn't show compensation of the forces due to the Earth's magnetic field. The torsion beam tests, the high sensitivity can introduce errors, and interaction with the Earth's magnetic field varies with the twist angle. that is impossible to measure the T-force reliably. Both tests and the simulation suggest that the T-force does exist, and the strength of the T-force depends on field geometry. This is the page that contains the results of all the tests for comparison. And based on those tests, in my opinion, it is worth further investigation. That means it is worth building a lab that is 100% shielded from the Earth's magnetic field. Going even further, here's how I see the propeller's prototype being built. We take the magnet arrangements and tilt them like in a windmill and rotate the blades. That means pushing against quantum foam. However, I don't expect this to overcome Earth's gravity. And finally, here's my call to action. I'm looking for help, collaboration in vetting the theory, vetting the tests, testing in a shielded lab, and building the device. Thank you all for your attention, and I'm looking forward to hearing from you.
Awesome. Okay, then let me see. Mikolaj, we have returned. It worked.
Okay.
It worked.
Okay. But I couldn't comment. I couldn't join the comments.
Oh, I'm sorry. So actually, could I ask you to move your mic a little bit closer to your head, if that's okay? It's a little bit. It's a little bit faint. No, if you could, yeah.
Okay, like that.
Yeah.
I tested on Zoom and it worked. Okay, so that's all right.
Okay. Oh, and you know what? Part of that could be my sound. I'll turn my volume up too. So yeah. Let me see. So do you want to do? Let me bring the guys in. So before anything else, you have a PDF that you're doing also, right?
Yes, I dropped it in.
Oh, okay. You know what? Here, let me do this. So before we do that, so you can do the back and forth buttons on the slide share. Mm-hmm. So I'm going to take myself out. I'll be here if you need help.
Okay.
But yeah, if you want to run through that, feel free. We've got about half an hour left. And again, thank you so much for presenting this.
My pleasure. Okay, are there any questions? Comments?
Oh, okay. Sorry about that. I thought you were just going to run through so this is the same slide deck that you just presented
exactly.
on?
Yes.
Okay. Sorry. Okay. So let me do that. I'm going to take this out, and I'm going to bring everybody in. So before anything else, we got to give Mikolaj Baczynski an enormous applause. Thank you, sir. And please accept my apologies. I'm a little scattered. We are like right there on Christmas, so it's just chaos. But yeah. So let me see, for the guys up here, do you guys have any questions for Mikolaj? I'll start with Drew. Drew, go for it. Oh, you're muted. Oh, you're not muted. You just don't have audio.
Set. I hate technology. Utterly hate it.
No, I can hear you, man. Oh, okay. You sound great.
Great, good. Sorry about that. Awesome presentation. Is there any possibility we could substitute the word static fields every place that you have magnetic fields? Because I loved everything about your presentation, except the whole magnetic thing. Because we've done everything you've literally stated here, but we've done it's with static fields. So
what do you mean static is electric field?
Yes, static electric field. Yes. So
but you cannot
electrostatic field.
But you cannot do what I did with the electric fields because of polarization. You cannot have two plates of the same polarity and different thing touching each other because they would be inducing. That's my point. I mean, I agree with you on that because I think we're basically using the same thing, but you cannot do that with electric fields, that you can have two negative or two positive touching each other because of induction, of polarization. in materials.
Yeah, I wasn't talking about that. In our propulsion system, we have a ground plate, which is whatever, a negative plate, and then a positive plate. And we have nothing but a static electric field between them. And we're achieving all of the things that you're trying to achieve, but we have zero magnetic component. So that's why I was wondering if this all could be explained using a static electric field instead of a dynamic magnetic field.
Well, this is not dynamic magnetic field. However, we see what happens is with magnetic field, it is what I've shown. But with electric field, there is things like vacuum polarization, like Schwinger effect, and so on. So there some of it may be similar, but again, the interaction with the basic quantum form of electric field would be different than with magnetic field, because magnetic field using the right-hand rule for the electric field is different. But I mean, again, it may be because you have to have varying. If you have the same intensity of the field all along, you will not achieve anything. But if your field is has gradient, then you can.
Yes, we have a gradient static field, so there's no magnetic component to it. It's all electrostatic field, and it has a very high gradient to it. So would that satisfy all of your initial conditions for this propeller thing?
It would, except for you have to take, as I said, in my case, there's no vacuum polarization. In your case, there is. So you have more effects than me, because my
well then we have your thing working.
Okay. Well, but are you trying to rotate your stuff or not? You see, that's
we've done that. Yeah, we've been around. Yeah.
Okay. Anyways,
we've extracted energy out. We've gone over unity.
Okay.
I really like the concept of pushing off that foam, that quantum foam thing.
But again, I mean, you may have two effects, both what I presented and vacuum polarization as well.
Okay. All right. Thank you.
Okay.
Awesome. Well, Drew, thank you. Jared, go for it, sir.
Yeah, I have two questions for your thing. The first one, I don't know if I missed a slide or something. Have you quantified the amount of thrust to the strength of the magnetic field?
No, I have not.
Okay.
And I can put that slide deck back up if you need it. Sorry.
Let me get to the second question, and then we can go to it. The second question, so for your windmill version, your propeller version, have you looked into doing any magnetic shielding in between the opposing spokes so that you don't get unwanted interactions? Like if you had a bunch of magnetic shielding in the center of the hub.
No, but what happens, what I did measure is basically how far away for the given magnets that I have, what's my shielding have to be, because you can shield against the Earth's magnetic field, but you have to shield against your magnets, okay? So I did some measurement, and I think if I have a lab that has basically a cube of basically 16 by 16 by 16, and I put the stuff in the middle, I can basically have both Earth's magnetic field and the interaction of the magnets with the walls basically nullified. But it would have to be that one.
That's 16 by 16 what? Centimeters
feet.
Feet.
And again, if you increase you can increase your magnet strength, and that would work that too, because of R square effect rather than. So basically, for the strength of my magnets, I think the minimum distance would be, I would say, 5 feet. But if you want to increase, have more magnets, I think 8 feet would be would be safe.
Couldn't that be miniaturized though if you blocked the magnetic fields?
But how?
With like mu metal, that's what magnetic shielding material.
I know, but your magnets would interact with the mu metal. Okay, so but you have to take that into account. The shielding, Earth's magnetic field is very weak, so you can easily shield it, but you have to also shield against your your magnets. So that's why the distance, I measured that distance. The minimum distance would be 8 feet for the basically this N55 magnets or so. Yeah.
Okay.
Oh yeah, Horst, go for it, sir.
I have a more basic question because I'm not so informed about your experiments. What is the counterforce against which your magnets should rotate? Is it the quantum foam directly which is against it? This will work, or is it anyhow hidden in your apparatus?
I'm lost. What do you mean? There's nothing hidden in my apparatus. It's just Earth's magnetic field and the magnets. I'm not sure I follow your question.
Yeah. Okay. You have magnetic fields in all parts with north and south poles, and what is the basic idea? How do you obtain a net force of in total? Is it the magnetic field which itself acts against anything, so that you get a net force in one direction, or how was it meant? Sorry, my very basic question.
Okay, so basically, I'm interacting the magnetic fields that I have, and the momentum of the virtual particle is transferred to that field. And if you move the magnets, you're pushing against that field. So basically, you're transferring your momentum as well, basically. So it basically that's how it is. If you leave it alone, the thrust is very small. But if you start spinning and pushing the magnets against them, you basically having your momentum of the magnets basically adding to the magnetic momentum of the quantum foam popping in and out. That's the idea.
Yeah, I see. Yeah. And the goal of you is to utilize the quantum foam as a counterpart for the motion or for the magnetic field, so that you get a motion. I understand. Yeah.
Something to push against. Yeah.
Okay. Thank you.
No problem.
Awesome. Yeah, thank you. Do you guys have more questions? We've got, let me see, we actually have about 20 minutes left, so. Okay, well, I think, again, we are right there on Christmas. What I'm going to do in the background here is I'm going to send out a StreamYard link and invite some more folks on. So let's do this. Let's put our hands together for Mikolaj Baczynski. Mikolaj, thank you so much for presenting. Thank you so much. And thank you, and thank everyone for joining us again. Like, we are so close to Christmas that, everybody is just in total chaos. I know I have, it's trying to get everything wrapped and everybody taken care of and keeping everybody happy, right? But, it is wonderful to be able to do a conference today. So, well, let me see. So, Horst, I think you are up next, sir. And
okay.
Yeah, so let me, I'll take Mikolaj out, and then, Horst, did you have something you wanted to upload? Did you have a presentation PDF?
I sent you a PDF, or I am not familiar with proceeding here. How can I switch between the slides then, or?
If I upload it, the reason I asked was if I upload it, you can't, but what you can do is, and I'm just downloading this now. Okay, there we go.
Okay, then
So what I'm going to do is upload this very quickly. Okay.
Upload. There's the upload button.
Yeah, well, it's so in StreamYard there's a present button, and I can put this up as well. Here's concepts for anti-gravity, and it looks like you got about 35 slides. Do you want to just run through this and And I'm going to take everybody else out. And then I would say I will be here in the background. Do you want to just say next slide when you're ready?
Yeah, okay, that may be the easiest way. Sorry for this complication here. So I can look at my own slides.
Oh yeah, no, that's totally cool. And I have a zip file also. I should mention that before you get started. And let me see.
The file contains only additional documents.
Yeah. Well, and the thing that I'm really excited about is, so Einstein-Cartan-Evans, right? Myron Evans, developed that as an extension to the Einstein-Cartan theory, if I understand correctly. But that ties into torsion physics also, and that's something that a lot of people have been asking questions about recently. And so, that was why I reached out to you, because torsion physics is one of those areas where a lot of people are excited about it, right? Even stuff like, Alexei Chekurkov's Graviflyer, he describes torsion as playing a role in that. And so you are one of the experts in that area. So thank you. Thank you again.
Okay,
So so just, I would say get started, and I will be here in the background, sir.
Okay, then let's start. I want to present some concepts, how anti-gravity can be understood and possibly applied if one knows how it works. And to get new ideas in this field, it's necessary to extend existing theories. And we did this with our Einstein-Cartan-Evans theory, and I want to tell you how this can be done and what torsion effects also will appear. And next slide, please. The content is I will shortly introduce this unified field theory, ECE, Einstein-Cartan-Evans, but only explain the basic points which are important to understand gravitation, for example. The potentials and the ether. What we call ether is the quantum foam, I think, of what we heard. Torsion and curvature play a role in space-time structure, which defines the ether and the potentials. The equations of motion are basically the Maxwell's equations, but are symmetrized in our case, so that these have more information than usual. Then I will come to the intrinsic field structure, what a field really is, and in particular we have to have an idea what a gravitational field is in order to be able to shield it or modify or impact it in any way. And we need special fields for this called Beltrami fields. I will explain what this is, and finally I will give some methods how this shielding of gravitation could be realized. Okay, next slide, please. Yeah, we at the Alpha Institute for Advanced Study, IIAS, I didn't write down the name here, developed unified field theory. That this means that all principal fields of physics can be explained from one root, and this is a classical method, not principally quantum based. Quantum theory comes also out of it, but in the simplest form, we do not need very progressed things like quantum chromodynamics or whatever. Normally we stay on the classical level of classical physics. We use the four-dimensional space-time of Einstein, and this is not enough because the French mathematician Élie Cartan had found in the 1920s that besides curvature, also torsion is there in these curved spaces, and Myron Evans found that torsion is always connected to curvature. You cannot separate it principally, so you need both to have a complete description of the 4D space which we use for this Einstein-Cartan-Evans theory, which can be considered as an extension of Einstein's general relativity. And this extension gives chances for new discoveries, new applications. Next slide, please. Yeah, here the protagonist, the three ones, and as I already said, we use space-time as a four-dimensional continuum. It's a geometrical model, so that we can say all which comes out is based on geometry. And one point to interpret this is that this space-time structure is identical to what also is called vacuum structure or quantum vacuum or either. And so we have a direct interpretation and are not restricted to abstract mathematical concepts where nobody knows how they have to be interpreted by physics. Next slide, please. Yeah, here as a short demonstration, curvature is, from surfaces of spheres, for example, where you have curved sections, triangles, and so on. And what is new here in this theory that also torsion plays a role, so that space-time spinning, for example, can be described by such helical structures. Okay, next slide. In physics, we speak of four natural forces, two macroscopic ones and two microscopic ones, or on quantum level. The macroscopic are electrodynamics, Maxwell's equations, and gravitation as a second macroscopic equations which are known everywhere. So, but we have extended, or let me say that in a way that from ECE theory we obtain formally also Maxwell's equations for electrodynamics, but with torsion built in. So this is an extension which comes from the Cartan geometry part. And gravitation, the equations for gravitation, later I will show them, are formally identical to the Maxwell equations, but with different constants, so that we get a gravitational field and not an electric or magnetic field. And we will see in a couple of moments how they are connected. The other two forces are the weak and strong nuclear force, and these come from the elementary particles, models, and yeah, the weak nuclear force is electromagnetic, which is also known in standard physics. Concerning the strong nuclear force, this is has a very short radius, is short-reaching force, only on the scale of nucleons, but we were able to show that this force can be described by quantum mechanics with some extensions of general relativity. So this is not a basic, not a principal extra force of nature. So that we can say electrodynamics and gravitation are the main forces, and with these extensions I mentioned, all forces are unified. This is our unified field theory. Okay, next slide. Yeah, and now let me come to the structure of the space-time itself. We know that there is a vacuum which is not empty. It's known by the Casimir effect. And our ECE interpretation is that the geometry of space-time shows directly its structure, and this can be denoted by either or non-empty vacuum, so that we have a direct mathematical description of this background field, which is not possible in quantum mechanics, for example. This result comes out from this E theory by certain axioms which have to be made first to connect the abstract geometry with physical quantities. So these are axioms, but one can see that they are quite natural and not artificial in anyhow. And the statement is that the ether is identical with electromagnetic potentials. And the second axiom, which follows from the first, is that all force fields follow from potentials of this background ether, similar as in electrodynamics. So if we speak about the ether or vacuum, we speak about potentials in this space-time. Principally, this should be kept in mind. Okay, next slide. Yeah, explanation of force fields. Yeah, we know that electric and magnetic fields or gravitational fields are present in the whole space of where sources are present, and we know the rules how to operate with these fields. These are Maxwell's equations, for example, but nobody can tell you what a field truly is in its nature. What does it consist out of? So it's not normally there is no answer to this question in the contemporary science, but we could, by ECE theory, could make some explanations of the internal structure of fields, what fields really are. And this is a completely new finding, which is important to understand the mechanisms, how fields, these force fields are embedded into the background either. For example, a magnetic field, as is known from each textbook, can be written as the curl of vector potential A, but nobody can tell you what the nature of this vector potential is. But we can, and this is described in the next slide. Yeah. The potentials that we know are the scalar potential phi and the vector potential A, and the scalar potential corresponds to an either pressure. It's a pressure expression, and the vector potential is a flow velocity. So the definitions of standard physics for the E and B field can be interpreted in this way. I already mentioned that the magnetic field is a curl of a vector potential. This means a curling ether flow in principle. The electric field is a gradient of a scalar potential. It means a pressure gradient, and there is an additional term with time-dependent ether flows, which also contribute to an electric field. This is our interpretation. So, and even these equations, although in this form directly known from standard physics, come out by our ECE computations, but with a completely extended interpretation of it. Yes, next slide, please. Yeah, these I talked about force fields so far, but there are also ether flows without force fields. This is a new aspect. For example, or let me say, these ether flows can be compared to a flow of liquids, and there you have also a pressure and a flow velocity, and it's the same here for this ether background. And if you have a laminar flow, there are no vortices and no divergence, and the same holds for certain kind of ether flows. They need not to have a vorticity or a divergence, and so these are smooth flows, but have a meaning of their own. And this has already underlined by a statement of Kenneth Shoulders. Please, next slide. And let me cite this. There appears to be an incredibly large number of useful phenomena yet to arise from using potential effects that are not immediately accessible to the force of E and B fields. These phase-determined force-free world will certainly be another chapter somewhere in the future, and I think also in this group here we are dealing with these aspects here. So this is a new kind of doing research and finding applications which are not known in this way so far. Okay, next slide. Yeah, now let's come to the question what these force fields really are, what is intrinsic of them, by what do they consist. For this, we use an alternative description which comes out from ECE theory, from the spinning of space-time, one could say. There are so-called quantities, called spin connections, and the electric field in this kind can be described by a gradient of a potential again, and a scalar spin connection function multiplied by the A potential, the flow vector, plus a vector spin connection multiplied by the phi potential of the E field. So this is an alternative description which can be transformed into the conventional one I showed earlier. But to understand what an electric field is here, it's important to use this representation. And in the electrostatic case, this formula simplifies to E equal to a factor times scalar spin connection times A field as an ether flow. In other words, an electric field is a flow of either particles or smooth ether flow if you consider it on a continuous level. This is a completely new result which we found, and so we can say what such a field intrinsically is. And for the magnetic field, it's similar. It's a vortex of the vector potential of the ether flow. Next slide, please. Yeah, and this was the structure of the electric field. Now we come to the question, what is common to electromagnetism and gravitation? Are there differences, or can it be seen as two aspects of the same physical basic structure? We know the Maxwell equations, Gauss law, Faraday law, Coulomb law, Ampere-Maxwell law. I think it's sufficient to call it by name here. And from our theory, the same equations in principle come out for gravitation. There is this well-known gravitational field G, which is the only one which is normally used or even known. But in addition, there is a gravitomagnetic field called omega, and this corresponds to the magnetic field, while the known gravitational field G corresponds to the electric field. You can see this directly by comparing these equations, and you see that the electron charge density, ρe, has a counterpart of the mass charge density, and the same for the current density, J in the electrical case and Jm in the gravitational case. So and I have to add that only one of these four gravitational laws are known so far or used so far. Sometimes there are approximations of Einstein theory where also a gravitomagnetic field is mentioned, but it's not introduced in this clear and principled manner as it is here in this theory. So we see that in principle, gravitation does not look different from electrodynamics, and so there's a high similarity. Let's go to the next slide. Yeah. So the geometric equations of electromagnetism and gravitation are the same, besides the constants which define the physical units of the fields. But there's a difference that the gravitational field is smaller by 21 orders of magnitude than the electromagnetic field. And this makes the difference so that so far both have not been considered under the same viewpoint because the orders of magnitudes are so different. But the consequence is that it's not certainly not wrong to assume that gravitation is also electromagnetic, and this is explained in the next slide. I told you that the electric field is a flow of ether, and when we have an electric charge, you know that when the electric field is radial in all directions, and this means that there is an ether flow away from this charge in all directions. But if the ether is depleted in the region of the charge, what does then happen is the question. Is this region emptied? But this cannot be because the ether is a space-time background is everywhere and cannot have holes or so. So the only possibility is that the ether particles, let's speak of particles, for example, like Tesla, the particles which are spread out or flow out of the charge have to be refilled from a stream which comes from outside and goes back to this charge. And this backflow of ether, this is interpreted as the gravitational field. It's also radial in this case, and this explains the similarity between the Coulomb law and Newton's law, where the force fields are proportional to 1 over distance squared. And this gives a consistent view of both electrodynamics and gravitation. And this is our interpretation on which we base further considerations. Okay, next slide, please. Yeah, gravitation is a special form of electromagnetism in this view, and the consequence, we want to come to ideas how anti-gravity can be realized, and so the idea is that gravitation should be influenceable by electromagnetism, because both is electromagnetic in nature, and as you know, several fields can interact and impact their structure, and this should also then be possible to gravitation, to impact it electrodynamically. This is the idea. Okay, next slide. And hey, how can we achieve this? I give you 4 examples. Biefeld-Brown, I think, is well known. Radiation on matter, counter-rotating fields, and shielding, direct shielding of gravitational radiation. And let's go into these 4 points and see what is meant by them. First, please, next slide, is the Biefeld-Brown effect. I think I need not much tell about this, found by Thomas Townsend Brown in 1920 with his assistant Paul Alfred Biefeld. And force is created or induced if a high voltage is applied, and this gives a force on the matter of the material, which are the electrodes of a capacitor, for example. And yeah, the effect is larger when the electrodes are asymmetric. Negative electrodes have to be larger than the positive one, and this gives the highest thrust. And I think this is already a known effect. The next slide, please. The Biefeld-Brown should not be confused with iron wind effects. For example, the lifters work in this way. They lift up due to motion of ions in the air, and not due to the true Biefeld-Brown effect. And if you look into Wikipedia, you see that Biefeld-Brown is explained probably as an iron wind effect, but I think it's not true. And Biefeld-Brown is obviously applied in avionics applications, if you know the details of this. It is not a true modification of gravity, because the electric field exerts dynamic effects which are mechanical. It's a mechanical force, and does not impact the gravitational field as such directly. This should be beared in mind. Okay, next slide. Radiation on matter. This is, I don't know if you have heard of this. It sounds very exotic, but experiments have been carried out in the 1950s and have described in several journals of avionics. So this was proven that this effect exists, and it appears when you irradiate a matter with electromagnetic waves in a certain range, wavelengths 0.3 to 4.3 millimeters, or a frequency range 70 gigahertz to 1 terahertz, which is the upper radar range. And this is described, for example, in the book of Keter, which I mentioned in the document zip file. But this effect results in a true reduction of gravitational force. The body which is irradiated gets less heavy, which can be measured, but I could not find any details on this anywhere in the internet. So if someone of you has some info on this, it would be interesting for me. So this was with radar effect on matter. Next slide, please. The third example how such modification of gravitation could be achieved is by counter-rotating magnetic fields. Here we use an effect of extended electrodynamics, the extension by ECE theory. Besides the electric current and charge density, we also have charge density of a potential, for example. In this case here, the Faraday is given. The classical one is time variation of V plus curl of E field equals 0. That's the basis for electromagnetic fields, for example. But in the full EC description, there's also a term at the right-hand side, and then the right side, the currents normally can be found. So there should exist a term called V, because by the physical dimensions, it is a current density of a potential, a flowing potential. It's a bit difficult to imagine, but I think that's correct. To simplify this equation further, we can neglect or provide that the electric field is not present. Then we see that the time variation of a magnetic field directly gives this potential current density. And how this could perhaps be achieved is shown in the next slide. Yeah, this is the patent application of Charles Callum there we spoke about some time ago. To counter-rotating magnetic fields. If these B fields here rotate, then the tops of the vectors move on a circle here, and the upper one in the left direction, the lower one in that's the same direction. Not sure if this is it is, if it's there. I think it's depicted in the wrong way, but anyway, the rotation must be in counter direction, and then this potential density V, which I mentioned in the previous slide, is produced because we don't have any electrical effects here. And in the volume of interaction between these two rotating fields, there is a compression or distortion of space-time in any way, and this is a candidate to produce anti-gravity or also other effects, which is not known, but one can expect that some interesting things could happen in this way. I guess that the magnetic fields have to have a certain minimum strength, otherwise you won't see something, but I think it's an interesting experiment. Okay, next slide. We come to the shielding of gravitational radiation. We have seen that gravitation is a radiation in principle, and such radiation should be shieldable. And the idea is to do this by localized electromagnetic fields with high intensity. And the question is, how can we construct such fields which are very localized and do not spread out to the whole volume we are working in, but have a high intensity? And the best candidates for this are so-called Beltrami fields. These fields are known for over 100 years in fluid dynamics, but have never been considered in electrodynamics. But the mechanism is the same, and these fields are even solutions of Maxwell's equations. So all the theory is okay in this case. So what are these Beltrami fields in detail? The curl of a field is normally assumed to be perpendicular to the field itself, as is the case for electromagnetic waves. But it's also possible that the curl goes into the same direction as the field. So it's a factor kappa times the field itself, and this is the Beltrami condition. And sometimes also scalar fields this comes up in this connection, but it's an unclear definition, and it should not be named in this way. So this makes no sense. Okay, but these Beltrami fields are good candidates for shielding effects, and let's see how this could work. First, we have to get a closer look how these Beltrami fields look like. Next slide, please. As you can imagine, if this Beltrami condition should be valid, then the fields have to be a lot of different directions in space, and so have to have a very special form. And these are two examples, and the right example was derived from Bessel functions from the mathematics, how they are created, and this is when they are a little bit smoother and also better to handle. Next slide, please. On the left, we see such Bessel function field decomposed into longitudinal and transversal components. The blue arrows are the longitudinal, and the red ones the transversal components. So you see that in the middle of the structure you have mainly longitudinal components, and in the outer regions also more transversal components. So this is a mixture of both types of waves. It's also interesting to consider the streamlines of such a field. A streamline is a line on which a small volume element or even a particle would move if it's in such a field. And you see that the outer region, the motion to the top is quite slow. It's more circular. But in the more you come to the middle, the faster move the particles, or even the field expansion itself, which can also be described in this way. So this is a typical Beltrami field structure. Next slide, please. And this is also not new. It's known from Schauberger, who investigated water flows in rivers, for example, and he found such motionless structures. And also in pipes, you can create by rotation such types of flows, and electrodynamically it would look like this in the same way, but has not been considered so far. Yeah, next slide, please. These Beltrami fields have certain properties which are not very known, or not quite unusual, let me say. All fields are in parallel, not only the E and B fields, but also the generating current density and even the vector potential A. These are all in parallel. it are standing waves. They are no have no propagating wave nodes or so, but they stay at this place where they are. And yeah, maybe it's not clear to 100%, but as I myself think that this structure, if it's modulated, then the modulation takes place simultaneously without any loss of time, because this is a standing wave structure, and mathematically this should be possible to be shown. And this is a very unusual behavior, and by this you can realize action at a distance, what Einstein criticized for quantum theory in his time, because he thought it would not be possible. But with this type of waves, it is possible. And even the quantum entanglement, where you have effects which are also propagating simultaneously or with no transfer time, can be considered in this way. And I personally always say many effects of which are thought to be quantum mechanical can in this way be explained by classical methods. So the meaning of quantum mechanics is a little bit reduced or shifted towards classical physics, but this only as a side side comment. Okay, next slide. Back to antigravity. How can we use now these Beltrami fields to realize structures which are screening gravitation? I already said that we need strongly localized fields for this, and have to create such Beltrami fields, not in volume as I showed in the examples so far, but on surface regions. And how this can look like is shown in the next slide. A screening of local structures. We have to create such a shell or something, such a surface region which contains these Beltrami fields, where E and B fields are parallel, for example. And if these fields are strong enough, it can be assumed that gravitational radiation is scattered and does not go inside of this screened region, and this means the masses therein become massless, because there is no, in the ideal case, there is not any gravitation present anymore, or at least this is reduced so that it can be, this reduction effect can be measured. So this is a basic idea to how to apply Beltrami fields for screening. So on the next slide, we see some ideas how to realize such a screening. It's not so easy, because you first have to define a suitable Beltrami structure, and yeah, you have to compute them in such on such surfaces. Simplest case in a spherical shell, and but there are some papers out in which such surface Beltrami structures are discussed, and yeah, possibly examples given, but it's not so easy to understand. But this gives hints how we can proceed to find such suitable structures. In the papers, it's mentioned that surfaces of rings, spheres, or toroidal structures, and also the coordinate systems may be chosen appropriately. For example, toroidal coordinates, but these are very special mathematical points already. But one has to deal with a lot of mathematics to find such a structure or work it out. It's not a field where you can obtain ready or complete solutions. As a simple hint in the next slide, please, how this could look like or work is more. I don't believe that it will work in this way, but you can see what the idea is. You take 4 bar magnets and put them inside and outside of a cylinder, which is a magnetic conductor, iron cylinder, for example. And if you do it in this way with north and south poles, you see that in the cylinder, the fields travel from north to south on both sides, and it's known that the magnetic induction is much higher in the cylinder than in the outer region. So this could be a first idea how to realize such a gravitational screening. But inside the cylinder, there is also a stray field, because there's a north pole and a south pole, of course. But this is much lower than that in the cylinder, because of the magnetic permeability and because it's not concentrated on a small region here in the cylinder. So this may be a hint to imagine, to get some ideas how this could perhaps be realized. Okay, next slide, please. Which steps have to be made to come to such results? First, the possibilities for creating force-free shielding fields have to be made. Force-free means outside of the shielding area, the field should be negligible. Mathematical modeling of corresponding geometric structures have to be made, and these have to be simulated to see how effective they are, and but you can easily investigate alternative structures by simulation. This is the big benefit if you do this. And when you are content with results, you can design control circuits to construct or to create these fields and make an electromechanical design for the complete apparatus. So this is the step-by-step method in very high-level steps described. Okay, next slide. Not much left now. Not many left now. I think you know the device of Alexei Chekhov. he uses rotating magnetic fields and electrostatic fields, as I have understood, but additionally radio frequency signals via a Tesla coil, perhaps to bring the ether in a certain state that shielding is more effective. And ultrasound, I don't know for what this could be good, perhaps to generate certain vibrations which support the screening effect or correspond to the electromagnetic fields, but it's not considered here in my slides, these last two effects. Okay, next slide. I am at the end of my talk. Summary is unified field theory has been introduced and a bit described to show you that all forces of nature are contained in it. And this field theory offers the possibility to give an interpretation of the background vacuum or ether structure, which is identical to the space-time structure itself. Furthermore, I showed you that how fields can have or which intrinsic structure fields have, and explained this a bit so that you have an idea what a field really is. And for shielding of gravitation, you need fields without outer forces. For example, Beltrami fields, which I explained to a certain extent, because these are, I think, very useful in several ways of applying them. And finally, I showed you some methods of shielding gravitation, how it could be realized. Okay, that was it. Thank you for your attention.
Wonderful. Well, Horst, thank you so much. Now, you had some other PDFs too. Do you want me to put those up, or should we go to questions?
No, it's only papers which have to be
okay.
separately.
Okay, well, let me take this down. Let me bring the guys back in then, and let me give you an enormous applause. Guys, please give Horst Ekhardt an enormous
Thank you very
applause.
much.
Yeah, and do you guys have questions for Horst? I should ask about that.
I do. Are you aware of, except for the last guy that you showed, of experiments showing any results confirming these assumptions or theories?
You mean for special effects of predicted by ECE theory?
Yeah.
Not so far, not directly. We have explained some experiments, for example, with satellites, where this gravitomagnetic field was found. It was interpreted a bit different by the researchers who did these satellite experiments, but we could explain it quite well with our theory without big problems. This was one of the examples. Electromagnetically, we are working on finding a principal proof of this potential current. It's not so easy. It goes to the direction of Tesla's experiments. Tesla used this extensively, but he didn't have a theory for this. So we try to bring this together now.
Thank you.
Awesome. Yeah. And anybody else have questions? Oh, yeah, Curtis, go for it. And actually, I will be right back. I'm going to mute myself out for a sec. I'll be right back, guys.
Okay. Great talk. Question. I noticed you had put up the equations that showed basically the del cross E, for example, equals kappa E, and same thing for the magnetic field. I was wondering what is the units of kappa, because typically on the other side you
This
have
is because on one side the derivative Nabla is standing, so it must be 1/meter. So it's a space frequency. How is it called? And it's 1/meter. It's has a special name. I just cannot find it.
Yeah, because usually on that side you have like dEdt or dBdt, right? So it's usually differential with respect to time.
Yeah. In the other case, it's you can easily derive the units dB over dt. It's Tesla over seconds. It's volt per square meter, because the seconds cancel out in this case. Yeah.
I see. So really, if it's a changing field, that implies a changing field, but not a changing field, or something changing over time, multiplied by that field that looks like it could be I guess it could be varying, but that's interesting, because one of the things in Jim's work is I don't know if you're familiar with Jim's Woodward's work on the Mach effect, but part of it is proportional to the change in power over time. So dPdt is something that's in there that can cause that effect. So that's why I found it interesting that you had these units that are similar type of thing to power, right? Because you get dPdt in there. The second question I had was, I noticed that at the end of the day, you were talking about an effect that is a shielding effect, where internally the mass may be affected if you have a skin effect or some kind of shielding effect that impacts what's inside. What I found is very interesting is that's very similar, or is actually the exact same thing as many other approaches. So the talk I gave last year, which is based on the Mendel-Sachs theory, which assumes a background pair of gas of coupled particle-antiparticle pairs, is the so-called ether. And in the theory, the coupling of that dense gas is what gives matter its mass. So if you can basically, we know how to split apart particle-antiparticles, which is, you get some light or some energy, and right, you can get two gamma rays, and you split the pair apart. And when you split the pair apart, if you can send them, you have a positive electron and a negative a positron, and electric field will send it one way, but you need a magnetic field to send the other guy, turn it around and send it the other way, right, to get thrust. But at the same time, if you lower that background pair density, you're lowering the mass in the theory. So you only have to do that on the skin, right? So you can enclose the volume, send out, basically lower the background pair density with whatever fields you're using that can do that, and you get that basically potential of having almost no mass. I find it very interesting that the theory you're proposing here basically goes along the same lines and points at the same kind of.
Quite interesting. Perhaps let me add one point. The main difficulty is to impact the ether flow, because it's so fine and goes through each matter, so that the cross sections of effective forces is extremely small, but you can do it by laser light, for example. I was told that this is a possibility to impact the ether flow itself in one perhaps should think about this method. Perhaps one can use it in any way. Certainly not for completely shielding gravitation, but perhaps for other purposes.
Yeah, when you bring up lasers, there's actually one of the two methods that we have now. Of course, they're still high energy, but so you can take two gamma rays and you basically split up a background pair, create an electron and positron. The other way to do it is that you have a field with a laser field of high energy, and you have one gamma ray. So that's a nonlinear effect that can also produce a background pair and split it up. So that really points to the same direction. And like you said, it's a matter of like, okay, so this is like higher energy. You're actually splitting it up. Maybe we don't have to split it up, but as long as we can push it on it. And that's the thing. These pairs in the theory I'm working on, they're coupled, tightly coupled. So interacting with them requires high energies locally, right? That's the tricky part to get. So,
yeah.
Well, Horst, if it's okay, I had kind of some general questions. I wanted to ask about torsion. And the reason that I wanted to ask was this is something, torsion physics, right? It comes out of Einstein's unified field theory. I know that ECE theory kind of dovetails in with that. And again, I know that this is an area that you have studied. Torsion comes up again and again and again in terms of these nonlinear effects like gravity modification and bending time-space and all of those things. What are your thoughts in general on torsion? Is there a there?
Yeah, some scientists make theories with torsion. I know it from the Russian sites there are some papers on this, but the problem often is that they cannot say what the physical meaning of this torsion is. It has to have physical units and make an effect to other physical quantities. This is a certain problem I realized some time ago. While in our development, it depends. You have torsion and curvature connected together, and each torsion makes also a curvature and vice versa. And Einstein only used curvature, therefore his field equations cannot be true as to our understanding, but anyway, one can use the metric of space when this is independent of details of torsion or curvature, and then it's okay again. But your question was about torsion. We made two types of developments to derive the field equations of electrodynamics and gravitation, the unified field. One was to base it on torsion tensors. The basic is that it's mathematical, is the other equations of Cartan, and when you these are tensor equations, and when you take out the right components, you get vector equations, and these equations contain the torsion elements. And these torsion elements can be interpreted as E and B fields. So primarily you don't have any extra torsion also, but it's contained in the field equations itself. And there is also an alternative approach we worked out, which is a little bit more complicated, but Myron Evans succeeded in this. You, instead of taking out the torsion terms from the Cartan geometry equations, you can take out the curvature terms and replace the torsion terms by curvature, and you get the same equations in vector form, but based on curvature internally. So these are both equivalent, and as I said, torsion and curvature are connected, and so no wonder that both methods work. But for certain things to describe or to see, in my example, what an electric field is, you cannot use the Maxwell form directly, but you have to let the torsion terms wherein these so-called spin connections, which describe torsion in curvature, and then only in this representation you can see that an electric field is a flux of either. In the other representation with conventional potentials, you do not see this. This is the difference. So in order to obtain certain results or new findings, you have to look at these different representations of the same fields to see what is really behind them. We also computed these spin connections with omegas I had in the formulas in many cases, and could see how it looks like for Coulomb potential, for example. Then the spin connection which represents the torsion is simply 1/r. So it's quite simple. It's similar as the potential itself, but from the theory, it's a spin connection, not a potential. So it's a little bit difficile, perhaps, to see all these differences. But without torsion, we would not have found this intrinsic structure of fields. It's an important point.
Well, and I appreciate you sharing that. I had just wondered, I mean, like, again, Alexei Chekurkov, right, with the Graviflyer. And I think you have followed that project too, right? Isn't that something that you're kind of following?
I followed it with some colleagues at the beginning of the year, and last time we did not do too much on this, perhaps. But
I mean, do you think there is a debate, right? There are some people who think that it's an elaborate hoax, and then there are other people who are absolutely convinced that he's discovered some new coupling between, gravitation and spin. So I don't know. Do you think there's something there, or is it too early to tell?
Spin is on the quantum mechanical level, and the question is how it appears macroscopically. For example, the magnetic field is based on the electron spin in the solid, so this is such an effect. And spin waves and such things which then make also macroscopic impacts. And perhaps on this way one could think about certain solutions or certain effects. But the spin itself, it's quantum mechanical. This has to be
well, that's interesting. That almost reminds me of what Mark Sokol's working with the dynamic nuclear polarization, because I believe he's aligning spins also, and that's on an atomic subatomic level. So potentially there's a coupling there too.
On that level, maybe.
Yeah. Wonderful. Well, Horst, thank you so much. Does anybody else have any questions? We're about 5 minutes from the top of the hour, and
yeah, I had a quick question about those equations. Another question besides the unit kappa, but I noticed that there were no sources in those equations. So that kind of makes it hard to figure things out. Have you thought of like redriving them with sources?
Yeah, this is a good point. In our theory, sources consists of fields internally. So if the fields have a certain structure, they appear as sources macroscopically, but they are internal quantities and not external quantities. This is a big difference. In Maxwell theory, sources are external, and also in Einstein's general relativity, the masses as the sources are external, and this makes big problems with energy conservation, for example. But in our theory, we even have equations how the sources look like. In the last papers, we described this. This is partially, it's also done in standard simulations. For example, that the E field times the conductivity is a current. Is a current which consists of the E field itself. This is an example how this works with the sources, and also the Lorentz force appears in our complete source part in the equations, so that our version is complete, I think, and contains all contributions which can be split into conductivity and Lorentz force essentially. And yeah.
Okay,
But
so you
if
do
you
have
say, if you say it's not of interest for me, my sources are more or less fixed. When put in the fixed sources, it's also okay.
Okay, so you do have a source equation that you could use with those.
Yeah, the ECE field equations are principally equations with sources where the sources consist of the fields itself.
Okay, and if the sources are zero, are the fields zero in your theory, or do they still exist?
No, then the fields need not be zero. It's only the certain field combinations which make up the sources. This can be zero, but that does not mean that the fields are zero itself.
Okay.
Awesome.
Okay, thank you.
Curtis, thank you. So, Horst, let's put our hands together and give you an applause one more time. Sir, thank you so much. Thank you so much. Again,
it was a pleasure to talk to you. My English is not so good that you.
No, your English is wonderful. It's wonderful. It is wonderful. It is wonderful. Thank you so much for presenting. You have this tremendous expertise, especially in areas that a lot of other people don't. And so I'm so happy you were able to share that with us. So
okay, fine.
Okay. Well, so let's do this without any further ado. Let me see. I'm going to take everybody out, and I'm going to bring Mr. Harry Sprain in. And we're about 2 minutes ahead of the hour. Harry, thank you so much for coming back, man. So you have a big demo you're going to do for us.
Yes, I do. Can you hear me?
Yeah, I can. That is, this is awesome. I'm excited.
I had some problems in the old lab here today. Things are always at the last minute, something goes wrong.
Well, no, you know what? This is a beautiful device, man. This is absolutely beautiful.
So what we've got is CID on a torsion balance.
Well, Harry, let me do this before anything else. Let me take myself out, and I will maximize your screen. That way people can see it better.
Okay. I guess I should get closer. Okay, guys, this is CID. Stands for Centrifugal Impulse Drive. What happens is the magnets are held in equilibrium between centrifugal force trying to throw it out and the opposing magnetic field pushing it back in. So once it gets around to this point, it's thrown out in that direction, creating a little punch that way. And then instead of the magnet being slammed back in, it's held in, centrifugal force tries to throw it out and keep it out, but it hits the opposing magnetic field and it puts it back in, but holds it in equilibrium. It doesn't get slammed back in. So it goes all the way around and pop, comes out. Now, if I had just one spinning on the end of the torsion balance, it would just create gyroscopic precession and just move itself right along. but this one spins in the opposite direction. So that counters any gyroscopic force that could be introduced into the system. It's just a simple torsion balance. It looks like she's pretty steady. Let's see if we can get this baby to go. I'll get on top of it so you can see right down at it. All right, let me get my remote. Get the other remote out of here. Okay. It's still moving a little bit this way. We're going to stop it, make sure it's completely stationary, and there's no energy in it whatsoever. So we're going to wait a second. Okay. All right. Okay. Plug it up. Uh-oh. Why are you doing that? Bear with me, guys. What is wrong? Hold on. I'm setting up the remote control and it is not cooperating. Why is it just turning on? It's not supposed to do that. We've got a problem, people. Holy shit. Come on. You were just working perfect. You were just working perfect. We got a problem, guys. Hang on. Shit. Why is it just turning on? Tim, we got a major problem.
Okay. Oh, sorry, maybe you couldn't hear me. Yeah, it looks like you're having some technical issues.
It was running just beautiful just a few minutes ago.
Well, you know, I've seen it in your videos also. So I don't think there's any debate about whether or not this thing works.
I know, but damn it, Tim, this is... Oh, I can't believe it. Okay, come on, work. I wanted to do it remote control so that I don't touch it at all. And it is just, I don't know what's going on. The motors are just turning on. Why are they just turning on?
Well, I'll tell you. So while you were working on that, I'm going to drop a link to your website into chat.
Yeah, you talk.
Yeah, and you know the other thing too is I'm gonna. In fact, if you want, while you're working on that, I could bring the guys back in. Let me bring the guys back in.
Yeah.
Hey Tim, why don't you show a video while we're waiting of what it is we will be seeing?
Oh my God.
And I'm just searching for YouTube right now. That's okay. Oh, here we go. Sid videos. Okay.
What's wrong?
Okay, so everybody, you should be able to see this. Yeah, there we go. Okay, so this is Harry Sprain's channel, And I'm going to drop this into chat for you real quick also. And he has a bunch of videos here. So let's go to this one first. Okay. And Harry, let me mute you out for just a sec. Okay, so you could see in that one it moved all the way to the tape line. Let me see. Do we have any others? I think we have some others here.
I just linked another one in the chat.
Ah, okay. Let me go to internal chat. Thanks, Jared. I'll put it in here because we are sharing. Okay, so there we go. Yeah, so that's two separate videos. This device moves. I mean, this thing moves. So, you know, again, what Harry's working on is absolutely amazing. Harry, how is your work coming along, sir?
We'll see.
Well,
What I
and no,
might do is I might just go run and get the other part where I can just connect it manually and adjust it. I know that works.
no stress. And you know, if you think there's going to be too much of a delay, we can go to something else and come back to it also.
Yeah.
Can somebody explain to me? I get it. So the magnet throws out or something, and you're stealing a little bit of momentum.
Oh, Drew, your sound went out again. Sorry, Drew, your sound is out, my friend. Oh, okay. Drew, for some reason, there we go. Drew, try and say something again. Your mic went out. Nope. Ah, okay.
Why does that just turn on?
Okay, and so I just messaged Steve Colbern, and I will see if he's able to hop on. He has some info that he can share for us. And so one of the hallmarks of APEC is live demonstrations, and there are lots of technical snags there. So one of the things that oh. Okay, I'm going to mute Harry out there. So again, what I would recommend is all of you guys take a close look at Harry's website. That's the qde-inc.com. I'm going to drop that into chat. Again, as you can see from those videos, these things actually work. There are other inertial propulsion devices out there that we've had several different variations that work. Now, like traditional science always accuses this of what they call slipstick technology, right? Where basically they're saying it shakes in both directions, but it sticks a little bit in one, which produces a creep in the other. But you know, anyone who's seen the Thornton canoe from the 1970s, I mean, that was an excellent example where it's a canoe, right? It has equal drag on both sides, and yet it moves directionally. And so you reach a point where it's like, okay, if this is slipstick, you know, why is it passing test after test after test? So you know, what Harry is doing is definitely part of an amazing heritage of ideas. And again, this is the website that he has, and the videos here. Oh, okay, yeah, and it's okay. It came up in a different window, so. Yep, and this is Harry's channel, and so again, guys, take a look. Maybe consider subscribing to his channel. You know, he's got a lot of stuff going on here. I'll put up a couple more shorts. Okay. Yeah, it looks like they're variations. Yeah. Okay. Yeah, they're variations on the same one. Okay. And let me see. Harry's still working on stuff. And if we can give Steve Colbern just a moment. Drew, welcome back, sir.
Thank you.
Yeah, now we have your audio. You were asking about.
I'm just trying to figure it out. When it's going around and you throw the magnets out, you gain some momentum from the magnets flying out or something. When you come back around, the magnets travel in and then are fixed. Whatever momentum you're stealing from the magnet flying out, wouldn't you lose that when the magnet comes back in, considering that you're transferring momentum to the center? I mean, those magnets are all attached to a spinny thing, and that goes to a center shaft. So I just don't get how you can.
I think you might lose some of it, but then, again, looking at the videos, right? I mean, he's obviously getting, directional motion, right? And it's consistent and it's repeatable. So now part of it is, if I remember correctly, the magnets move. So part of it is, I think when it comes back in, you're imparting mass a little differently.
He says he's got them spinning in opposite directions because he wants to counteract.
Yeah, you got to counter rotate. Otherwise, it'll just spin.
But they're not the same distance from the center of rotation of the system. One's about 2 feet from center of rotation. The other's about 4 feet from center of rotation. So they have very different.
Excellent point, Drew.
Yeah, that's a good point. That's a good point.
Here's what I wanted to ask.
That's one of the sticking points. But the other is, if you're getting momentum from the spinny part on one side, you're losing it on the other side. I don't get it.
Well, you would think, but then at the same time, this follows. I mean, I've seen so many different demonstrations of inertial propulsion devices, and all of them demonstrate movement, right? And so I think that's the challenge. What I love about Harry's, the quality of workmanship that he's done is amazing, And I mean, that's the same thing that you're doing down in yours, right? It's part of it is the workmanship.
I'm not picking on the guy. Just that it seems like you would desperately need to have servos so that those two things are spinning at the same velocity at the very minimum.
He might
otherwise
have some controllers there.
Just spinning doesn't mean you're actually canceling out the rotational components.
Drew, you have an excellent point, and I'll tell you what I wanted to ask. Because you have those two dudes on one side, but you should put them on both sides, okay, and then turn the other way around and do the experiment and then flip them. You see, because then they would neglect, or you would take into account what you just said, Drew. I think this is excellent. Then being on the same side, you have a point. Okay, and then there's argument against it. But if you put them on both sides and you swap them and you get the same effect, then you have a point. That's my 2 cents.
Yeah, I almost would. And again, I'm not picking on this guy because this guy does beautiful work, from what I can tell.
But absolutely.
It seems like you'd want the motors on a common shaft. You'd want to have a single motor, common shaft. I don't know if that'd help you any. I don't know how you'd spin it reverse. I think about that, but yeah, you definitely want them one on top of the other.
Yeah,
one spinning this way and the other spinning that way.
You use a belt and you put a twist in the belt.
Or something, yeah. I mean, yeah, you could. I mean, there's a lot of ways. You can do it electrically, but if you do it electrically, you really, really have to have this thing balanced. You'd have to know how much inertia each one of these things is providing, and you'd have to go ahead of time and balance the inertia of these things so they truly do cancel each other out, regardless of whatever speed they're spinning at. They actually have to cancel each other out absolutely before you can say, okay, I'm not imparting any rotation due to, well, I'm not even sure what it would be.
But that's impossible.
Gyroscopic effect, maybe?
Well, so yeah, I mean, you would think though, if there's an imbalance, you would see a torque. So I think, oh, Jared, go for it.
Well, I was going to say Jeremiah's over here in chat, and he's making some good points. In some ways, I wish we had Curtis still on, because in some ways it does have similarities to the Mega Drive. So that little magnet on the inner spinning part, that gets thrown out, right? And the amount of time that is getting thrown out, it's a very quick, very fast acceleration out that way. And then it gets pulled back in for a very slow acceleration for the remainder of that turn. And so similar to the Mega Drive, where you have one quick fast impulse and then a very, slow delay like return. It's kind of like that whole spike thing.
So this seems like it goes back to the Jeffimenko equation, which is something that Tom Vallone talked about recently. And I know like Paul Murad was excited about that. Several other people were really, I think Gary Stevenson were excited about Jeffimenko back in the day. And his thing was, when you have a quick jerk, conservation for some reason doesn't apply the same way. And so, I guess that would, in Harry's case, that might make you have large amounts of mass rotating quickly, but you have a small net effect. Maybe that is Jeffimenko, right? What Jeffimenko was talking about was large motions happening quickly. Here, let me bring Curtis back in. Curtis?
Hey there.
Hey, Jared was he was talking about you, sir.
Yes, I was here. I'm here in the private chat, but I would say I agree with Drew about making sure that there's not kind of mundane mechanical effects. Basically, I would agree that you want it at the same radius for that precession, canceling out the precession. Or if you calculate it, maybe they're rotating at different speeds, but really you want the same radius. And the other question I have is if they counter rotate one way and counter rotate another, does it precess the other way? That's a question I would have as well.
I think they're directional though. You see how you got that little kick out on the one spot. So if you go backwards, I don't think it's going to really.
Yeah, so it'd have to probably be installed to run the other way. But I'm curious if that experiment's been done. I'd be curious about that.
Well, okay, so they throw the magnet in on, like the one that's on the far left. It's rotating counterclockwise. So at around 7 o'clock, it starts to compress the magnet in towards the rotor, and then at around 4 o'clock, it just lets it fly back out. Is that right?
I believe so. But Drew, I think the thing to keep in mind too is, so right now he has this on a torsion balance, right? So that it can rotate. But if he put it on like a swing, based on what we saw in the videos, it should deflect a swing as well. So there may be some torque effects that play a role, but those torque effects wouldn't explain the net motion, And so what we do see is a net motion with it. And again, going back to Roy Thornton with the canoe in the 1970s. In fact, let me see if I can find that.
Yeah, the precession would be because of that counter rotating at different radii.
Could he put one of these things on each side?
That's what we should do. In my opinion, that's what we should do.
Yeah, he's got both of them on one side, which puts him asymmetrical to the center of rotation. Does he have any videos at all with one on one side and one on the other?
Yeah,
no,
I
yes. Don't think so.
Oh, well,
check it out.
On a balance, but on the table, no. On the table, yes. Okay, hold on.
But also you have to put them on both sides and then swap them, and you see if they're turning the same way, because otherwise there's no way that you're gonna be balancing them at all. It's too difficult because mine tiny things.
Yeah, and then the other thing you could do is you could just turn one. Oh, there you go. There's a canoe.
That's the Thornton canoe. Yeah.
Yeah.
So this was back in the 1970s, and he's using a mechanical inertial propulsion device. Now, I think, if I remember correctly, his is vertically oriented, Harry's is horizontally oriented, and in Thorsten's case, there was no magnetics. So it was actually louder. You can kind of see in there. It was louder, and there was a thunk, 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 thunk. But here, I'll replay that again so you guys can see it. But yeah, I mean, again, you can see he's cruising at a pretty good clip there. So.
I also have to wonder if on Harry's, how he has it on a table like that, and you got two gyroscopes on a table with a center like string holding it. If that table is getting tilted at all from those masses getting thrown out, now you got that gyroscopic force. It's going to like push against the string and then push back on those gyros, and so that could induce extra noise into your measurements.
Yeah, one thing to keep in mind, and this I always tell Jim, is that we got to be careful of nonlinear.
I got to tell you, if this has been around since the 70s, how come we don't see, this is the first time I've ever seen this. So I didn't see the thing in the 70s.
So
where's it then?
Yeah.
So this, again, this is on a table. This is not suspended, right? And so you've got drag from the table because it's just on a board. But it is a net directional movement. And it takes a while in this one, again, because there's friction, right? That it has to overcome the friction. But you can see it's going to move to the tape line. And if he had this on water and he did another test where it was floating on something.
Yeah, the problem with the table surface like this when you have vibration, because you are having vibration, is that you point at stick slip, right? So that's the issue with this.
Yeah, I got real problems with stiction.
And so what I was saying about what Jared pointed out, which is a valid thing, when you have a nonlinear equilibrium, that's an issue. But even if you have a swing, right? We all know you can get on a swing, and you can like make yourself swing, right? And the way you do that is you raise yourself in the gravitational field and you let yourself go down. So if there is a thing like that, like Jared is saying, when you're up here, you kick down, and you'll get a preferential movement. That's entirely possible if that motion is happening, but I don't know if it is, right? So one thing about hanging from a string, you want to have what we used in the lab for when we were doing it in air, hanging from a pendulum. The pendulum actually had 3 strings and was on a bracket to prevent us from having that kind of effect where it was a swing effect.
That's what I did to my torsion balance too, to eliminate that effect. Yeah, I agree with you.
Okay. Oh, and here is Steve Colbern. Steve is here, and you know what? It's 2:30, so I'll tell you what. Why don't I stop sharing? Okay. And so Harry is still working on things. So I think what I may do is take everybody out and then go into Steve's analysis report on metal samples. And Steve, do you want to upload that as a PDF, or do you want me to? Because I can just share screen.
Yeah, why don't you go ahead? I'm not sure how to do it here.
Okay, yeah, I've already got that up. So what I will do is, in fact, you know what? Here, I'm going to download it, and then I will upload it so it's even super higher quality. Okay, and so let me take everybody out, and again, we're working on things, and I will probably bring Jared back in at some point because Jared has been working on this, so he is studying it carefully. Okay, awesome. Yeah, and so it put this up as a series of, ton of slides, different pages. Do you want to just say next and previous? I can just let you do an overview of it.
Sure, yeah, I'll say next and previous. And
Okay.
well, this report is about some samples that I received from Mr. Chuck Wade at the UFO Congress back in 2009, and they were from the crash of a small extraterrestrial craft near on the plains of San Augustine, New Mexico, near a town called Horst Springs, and Art Campbell, a historian named Art Campbell, actually found the crash site a few years before, and then Mr. Wade came out there with a bulldozer and actually recovered several pounds of material that the military had missed. This was reportedly the first crash of an ET craft, and it was before Roswell, several days before Roswell. And I assume they hadn't perfected their protocol for recovering crash debris yet, but at any rate, there was more material out there. And he recovered several pounds of material and gave me some samples, 6 samples of different types of material from the crash site. Later on, a few years later, I took an expedition out there with some other people, with Mr. Wade and some other people, and we actually recovered. It's not the second expedition material is not in the report, but we actually recovered a honeycomb material that was very interesting, and it had these brown dots on it that I think are mechanical actuators that I'll talk about more in another presentation. I also talked to on the second expedition an eyewitness that came upon the crash site before the military got there, and he said it was kind of a horseshoe shaped craft about 40 feet across, and it had a rip in the hull, but was largely intact. And he said that there was a bunch of fiber material coming out of this crack in the hull that resembled fiber optics. And he said that right after he got there, the military showed up and shooed him away. And he said that he saw 2 dead aliens and 1 live one inside the craft before they got there. But anyway, next slide. Next page. So the analytical procedure was that I did low and high power light microscopy on all the samples, and then cut small flakes of each material off to do SEM, and we did SEM and EDX mapping and point and shoot techniques, and then I cut about a 10 milligram piece off of each sample and sent them in for ICP-MS, inductively coupled plasma mass spectrometry analysis. And so that's a technique where you dissolve the sample in nitric acid and send the liquid through a plasma torch and then through a mass spec. And we got the trace element abundances down to parts per billion, and also used the raw data to compute some of the elemental abundant or isotopic abundances for 3 of the elements in the sample, and that gave some very interesting results. I also exposed the samples to a neodymium iron boron magnet to see if they were ferromagnetic, and they were not. And ran a pendulum over the samples because Mr. Wade had done that and got some interesting results. And it almost seemed like the samples are giving off some sort of energy, but the pendulum seemed to be deflected a bit. But we'll have to investigate that further. Anyway, I'm getting ahead of myself. So appearance and physical characteristics of the samples, they were all shards of a silvery sheet metal, which resembled sheet aluminum, and the major component of all the samples was aluminum. These ET craft appear to be made out of, in general, this is a conclusion based on other analyses too, that they in general are based on some of the same materials or same metals we build our craft out of, except that they contain nanostructures and are kind of smart materials. Electronics and propulsion are sometimes built into the metal. All of the samples, with the exception of number 2 and number 6, had many ridges in the material and a crumpled appearance. So I don't know if they're manufactured like that, or if the crash did that to the samples. Gerald Anderson, the eyewitness, was saying that the foils, probably sample W1, were kind of loosely packed between between the inner and outer hull of the device or the craft, and so perhaps they were involved in producing capacitance or to produce a bifield Brown effect. I don't know if it might have been something along those lines, but all the samples could be bent by hand with the exception of sample W6. It was a bit thicker, and W6 also had kind of a layered appearance as if it were made by CVD deposition or something along those lines. Next page. Here are some of the pictures, light micrographs of sample W1. You can see the crumpled appearance, and the surface was very interesting. Some of these samples seem like they might have some sort of a coating on them. I wasn't sure if it was an actual coating or if it was soil adhering to the material. It seemed like a coating to me on at least a couple of them. And I thought those circular or oval shapes on the surface were very interesting. They could have been microstructures of some kind. It seems to appear very differently from aluminum of human manufacture. Next page. Here you can see that there's some sort of a coating on the material. This is sample W2, and it's very bright aluminum-looking metal underneath. And it could be removed with a knife, but it was bonded fairly well to the metal. Yeah, next page. And here's sample W3. This one had more of a bright appearance in many areas. And also you can see some microstructures that were smaller than on the first sample. It just looks very strange compared to most aluminum pieces I've seen before. But it's very interesting that the strength of these materials was not very impressive compared to some of the alien materials or possible alien materials I've seen before. By the way, I used to work for Dr. Roger Lear from 2008 until his death in 2014, and analyzed several alien implants that he removed from his patients. And so I've gathered from that also that a lot of these things are sophisticated nanotechnological devices, and a lot of them contain carbon nanotubes. And we'll see later that there's some indication that these St. Augustine samples also may have had carbon nanotubes, although it was somewhat inconclusive in this case. But there were some intriguing indications that there might be some single wall carbon nanotubes present. Next page. Yeah, this sample is very crumpled, W5. Mr. Anderson said that W5 and W1 might have been identical, but the analysis results, I believe, are also very similar. Next page. Here's the sample W6. There's the layered structure that I mentioned, and this sample, in my opinion, definitely had a coating that was applied. You can see that in the bottom two pictures, and it was bonded pretty well to the metal, and it just has the appearance to me of a sample that was made by chemical vapor deposition or some other technique along those lines. After this, we did the SEM testing. Next page. Again, we see some structures on the surface that look like they could be microstructures of some kind, possibly adding to the function of the material. One very interesting thing when we did SEM was that there was some sort of interference coming from the material. It was impossible to focus on these samples at much more than 15,000 times magnification. There was a charging problem, but also there seemed to be some kind of interference, as if the samples were giving off some sort of energy. And I saw that with the implant samples I analyzed for Dr. Lear as well. I get the impression that a lot of these alien materials are still functioning on some level, even after catastrophic self-disassembly and removal from the device that they're originally part of. That would make sense if they are nanotechnological devices and have nanostructures and electronics built into the metal. Next page. Yeah, there's sample W2. This one appeared to have a thicker oxide coating under SEM, and maybe fewer of the possible microstructures. Hard to know what to make of some of this stuff, but it's very interesting. Next page. Another sample. This looks more similar to the first sample under SEM, and some of these samples had ceramic-like crystals and pits. It's uncertain if they were deliberately introduced or were there as a result of some sort of weathering, but I have a feeling they were deliberately introduced. I saw an implant sample that came from Dr. Lear's patient 16 that had pits that were definitely deliberately introduced. So that may be a technology that they use. In fact, I get the impression that nanotechnology in general is old technology to the aliens, and it's things that we're just trying to do just now in the lab for the first time, or things that they've done for perhaps thousands of years. One thing I realized in the course of this research is that I thought going into this that the aliens were maybe less than 1,000 years ahead of us, but I don't think that's the case, because I had some strange experiences after working for Dr. Lear. I also met Dr. Lear because I had a mysterious object appear in my toe after a possible alien encounter. I went to see Dr. Lear, and he x-rayed the toe and found out there was an object there, and he wanted to remove it, and had it removed a few months later. And it was a sophisticated nanotechnological device. And anyway, what I'm getting to is that I went to his office before the surgery to get some tests done on the object and see if it was giving off radio signals, which it was. And he pulled my x-ray out of a stack of x-rays to look at it again, and the x-ray of my toe. And it seems like the aliens like to show off their technology sometimes, because we both couldn't believe it. I knew something was wrong, because when he pulled that x-ray out, his jaw was practically on the floor. And I go, "What's wrong?" And he goes, "Well, see for yourself." He held up the x-ray, and the lettering on the outside of the envelope that the x-ray was in had somehow been transferred to the developed x-ray film. I mean, I don't even know how you would do that in theory. There's no theoretical basis that I can think of that would account for that, how they would do that from a distance and with the x-ray in question and a stack of other x-rays. It is very strange. I've seen some other odd things that lead me to believe that the aliens are much more advanced than I first thought. But anyway, I digress. Next slide, or next page. Yeah, this is W4. This has a little bit different surface texture. Fewer obvious microstructures, but anyway, people can draw their own conclusions as to what those might be. But those crystals on the upper three pictures look like they could even be some sort of micro antennae, or I'm not sure, but I'm not sure if that's deliberately introduced again, but I suspect they might be. Next page. And this sample has some of the pits I was referring to before on the bottom two pictures. And picture number 4. Those are very interesting pits that look deliberately introduced. This sample is a bit smoother than the others. Sample W5. Doing the SEM shots, it seemed like sample W6 was giving off the most interference, and as I recall, and could not be focused on at very high power. Next page. Here's sample W6, and you can see the layered structure again in this, and it would be very interesting to do electrical measurements under SEM. I think that's possible nowadays, but that's really high end. We weren't able to do that during this analysis, but I think that with some of these samples, doing electrical measurements under SEM with various parts of the material, seeing if there's anisotropic resistance for different resistance one way versus another in the sample, and perhaps doing fast atom etching followed by EDX mapping to see how the structure varies with depth in the material would be very interesting to see if there's a 3D structure to it. I strongly suspect that there is. In fact, I've seen that in another sample with that came from a crashed orb from Mexico that was turned out to be a titanium sphere with carbon nanotube electronics inside the metal. Next page. EDX data. The EDX mapping indicated that the elements in the materials were pretty well homogeneously dispersed, and the coatings on the metals were different than the metals themselves. There was a little more silicon, titanium, and nickel in the coatings, as I recall. Next page. Yeah, here's sample W1. The surface had, more nickel and phosphorus, oxygen. So oxides and phosphates and chlorides, perhaps. There's some sulfur in the surface coating as well. So, next page. Here's EDX mapping. The elements look like they're pretty well homogeneously dispersed, with the exception of the silicon. That's some of those crystals or structures on the surface were apparently silicon dioxide. I also analyzed, Dr. Lear had a piece of what was said to be a piece of the Roswell debris that he got from a friend of his. And supposedly the last owner was killed under mysterious circumstances and given to this friend of Dr. Lear, who I don't remember his name offhand. Jim Fueling, I think his name was. I don't know if anybody even know him, but anyway, it turned out to be ultra pure silicon with some very strange impurities that were different than silicon manufactured here, and had a curvature to it. I think it might have been the lining of the reaction chamber, and probably meant to change the heat of the reaction into electricity directly. But I remember there was silver in it, which, you know, there's no silver in ultra pure silicon manufactured here that I'm aware of, and I have a report on that, so maybe I'll present that next time. But yeah, next page. Here's a point and shoot of sample W1 and three different spots. So that turned out to be fairly homogeneous, except there's more magnesium and sodium in one spot. So there's some inhomogeneity, but not a whole lot, I guess. Yeah, I think the bottom EDX spectrum is that little rock in the center, so that the structures have more magnesium and sodium apparently, and silicon. Well, now they're the top one has a lot of silicon too. Anyway, next slide. W3. This had fewer elements in it. Apparently, beryllium showed up. I'm not sure if that's an artifact or if beryllium was really present. I don't think the ICP-MS showed much if any beryllium, but we'll have to see when we get there. I don't think there was. Sample W3. Next slide. Yeah, no beryllium in this one. Very similar. Yeah, they were all very similar, but there were some differences. I remember I think it was sample W4 had the most iron, and there was another one with a lot of zinc. And next page. Yeah, they're all very, very similar. This is sample W5. Next page. I did two EDXs here on W6 because I wanted to show the difference between the surface coating and the metal. The W6 obviously had a coating on it, and I'm not sure why there was that big titanium peak in the EDX here. There wasn't too much titanium in these samples. That must be an artifact of some kind. Palladium showed up in this sample, and that's very strange. And a lot of chlorine in the coating part of it on the bottom, and so there were sulfur. So chlorides and sulfates, perhaps. Next page. And magnetic and electrical analysis. I tested all the samples with an ohmmeter, and they all conducted electricity, and none of them were attracted to a neodymium iron boron magnet. So they weren't ferromagnetic. I'd be surprised if they weren't a little paramagnetic because they had significant amounts of iron in them, but as evidenced by the ICP-MS. But I wasn't able to determine quantitative values of sample resistivities because the samples were sort of irregular in shape and thickness. But if we do any more testing, we could probably figure that out. And Raman spectroscopy, there was some intriguing indications there could be carbon nanotubes present, but I'd say overall it was somewhat inconclusive, except for sample W1. I thought at the time had the most indications of having carbon nanotubes present. The one sample that I analyzed for Dr. Lear, and it came from patient 16 that had the pits in it I was talking about before, also had the highest concentration of carbon nanotubes that I'd seen in all these samples. There was no question that sample had carbon nanotubes. I didn't see any carbon nanotubes on the SEM shots because apparently it was dispersed extremely well in the metal. The material was dispersed extremely well in the metal, and you couldn't see them. Probably they were probably present as individual tubes, but in any event, that material was incredibly strong, and it took a high energy laser to cut it. Diamond tools wouldn't cut it. We usually cut these samples in half to see the interior in the case of bulk pieces like implants, and regular tools and diamond tools wouldn't cut it, so we had to use a high energy laser, and that would definitely follow from the fact that there were carbon nanotubes present in the material, and they were highly dispersed in the metal. Carbon nanotubes are the world's strongest known material, and right now in earthly science, we're trying to make well-dispersed carbon nanotube metal matrix composites like that for high-strength applications. And since carbon nanotubes also have electronic properties and can be used as transistors and diodes, it's theoretically possible to disperse carbon nanotubes in the metal in a 3D structure and use them as electronics built into the metal, which I think is what the aliens are doing in a lot of cases like this. Next slide. There were some peaks in sample W1, which I believe later turned out to be peaks from aluminum oxide, but in the high frequency or high wave number region. But in the low wave number region, there were a couple of peaks that could have been single wall carbon nanotubes, and it'd be very interesting to dissolve some of this material in acid and see if any carbon nanotubes were left behind. If I were going to go back and retest these samples, that's part of what that was one of the things I would do. Carbon nanotubes are also very resistant to chemical dissolution or oxidation. They survive in air up to about 500 degrees Celsius or higher. And in vacuum, they'll go up to like 2,000 degrees Celsius. They're very, very stable and very strong. And you can change the electronic properties of them by putting different metals inside. I actually have a patent on that. They're conductive in such a small diameter that the Casimir effect can actually suck things into the interior of a carbon nanotube. I don't know if you're familiar with that, but it's a vacuum. It's a quantum vacuum force. If you have two, say, sheets of conductive material close enough to each other, it does not allow virtual electromagnetic radiation of greater than that wavelength of the spacing between the plates to propagate between the plates. And so there's more pressure from the 0 point energy outside the material than inside. And it leads to a very strong force pushing things together if two conductive materials are spaced closely enough. And that also applies to a conductive tube, obviously. Next page. Okay, now we're down to the ICP-MS analysis. We tested for 68 elements. You can't test for every element with ICP-MS, like iodine, sulfur, volatile elements are not able to be tested for. We detected 56 elements in at least one sample. I think that was sample W6, as I recall. And aluminum, of course, was the biggest contributor and most abundant element in the samples, and followed by iron, silicon, calcium, manganese, magnesium, potassium, titanium. And this is very unusual for a human. It would be very unusual for a human-made aluminum alloy. That's a lot of elements to be present. I think usually there's only like 3 or 4, or most 5 or 6 elements present in human-made alloys. And I've got a table later on of the abundances in each sample. Next page. Here it is. Here it is by sample, and it's more instructive to do it by average abundance. Next page. Next page. Here we go. So in all the samples, aluminum was the matrix material, the number one material, then followed by iron. 7,600 ppm of iron in W1, and W2 had 7,100, 8,800 in W3. Yeah, W4 had the most iron with 111,000 ppm. That's like 11%, I believe. And W5 had a lot less, 5,100 ppm, 4,500 ppm in W6. Silicon was a big contributor to 2,600 ppm in W1 and less in the other samples. I kind of hypothesized that these samples may have been acting as electrical conductors, and if so, perhaps they used iron and silicon for maybe for other reasons too, but because iron and silicon do not interfere with the conductivity of aluminum as much as other alloy ingredients would. We have calcium, manganese, magnesium, potassium, titanium, copper, phosphorus, zinc, sodium. It's hard to get a feel for all this without staring at it for quite a while. But there was some rare earths here too, which I found interesting. I heard a while back they were doing experiments to strengthen aluminum using rare earths. So perhaps that was part of the reason for their presence. There's gadolinium, praseodymium, neodymium, and a couple other rare earths, I think, too. Next page. Yeah, we have dysprosium. Dysprosium and I think it was ytterbium were present in those brown dots that we thought might be mechanical actuators on the honeycomb sample I mentioned. And europium. There's quite a few rare earths in here. A little bit of erbium, a little bit of iodine, samarium. Yeah. Very strange. Rare earths have very strong magnetic, a lot of them have very strong magnetic properties. Perhaps they're in there to alter the magnetic properties. It's hard to say at this point, but it's very difficult to think that strange to think that they would put all these elements in there without them having some definite purpose. I don't think that they have the capability to manufacture this kind of stuff back in 1947. And it's possible it could have been part of some top secret government project, but personally, I kind of doubt it. At a table there about the amount of iron, calcium, and magnesium on the different samples. W4 had the most iron, and a little easier to see that way. Next page. Here we go. Potassium, titanium, copper, phosphorus, zinc, sodium, W6 had the most zinc. Again, I'm not sure what that means, but it's very strange. There's that zinc's not a very common alloying element in aluminum. I've never heard of it actually. And sodium and sample W1, that could be contamination, I suppose. But I did rinse off these samples thoroughly before analyzing them. But they were buried in the ground for a while, so hard to say if that's contamination or not. Next slide. And I did isotopic analysis of sample W1 using the raw data from the ICP-MS analysis. And I've seen before that it's very interesting that the sample isotopic abundances are skewed in antimony, copper, and nickel. I use those three elements because there were no significant interferences with other ions or isotopes. And the isotopic abundances are very skewed compared to the terrestrial ones. On the right, you see the terrestrial isotopic abundances in each element, and then the sample isotopic abundances on the left. And in each case, you see that the heavier isotopes of that element are overrepresented in the sample, and they're extremely skewed compared to terrestrial abundances. Dr. Lear and I thought that this is way too strange and way off to be from Earth. It couldn't possibly be from Earth. In fact, it probably couldn't even be from the solar system. You can tell what celestial body each sample comes from, usually by the isotopic abundances, and they're off a little bit compared to Earth on like the moon or moons of Jupiter, or any place else in the solar system, asteroids that come down. But they're usually off by way less than this. I would say that either these samples came from closer to the center of the galaxy, where there's heavier supernovas that synthesized these things in the first place, and higher neutron fluxes during the supernova explosions, synthesizing more of the stable, heavier isotopes of each element, or they've been exposed to a very heavy bombardment of neutrons or other nucleonic particles. Either way, they're extremely strange, and I'd say this gives a very high probability that the material came from off planet. One very strange thing about some of these things is that a couple of times they seem, when I did the same test that Mr. Wade said he had done, that the sample seemed to deflect the pendulum. I'm not sure what's up with that, unless they're giving off some sort of energy, but we need to do further tests on these materials to see if that might be the case. I did the tests at the 2010 UFO Congress in Laughlin, Nevada. And next slide. I was left a little bit perplexed by some of these things. I mean, there were some indications that there were carbon nanotubes in the material, and but the mechanical strength wasn't too impressive, which was kind of surprising. That sample W6 had a layered structure, which was very strange and very unusual. So the isotopic analysis was very, very telling, though. I mean, I think that these have to be from off planet unless the data is completely off, which I doubt. We need to do more isotopic testing at other labs to confirm this. Next page. And the sheer number of elements in the material was very strange and indicates they were very unusual. And the rare earths, that usually don't see that in aluminum. They're very strange samples, but I was just kind of surprised that they weren't ultra strong or have other unusual mechanical properties. But then again, we don't know that they don't under certain conditions. I mean, we need to do more testing. There's a lot of this material available. Mr. Wade has at least a couple pounds remaining of this material, I'm pretty sure. And anybody that wants to get some of this material might want to contact him. He was very anxious to give away some of the material for testing last time I heard. Next slide. So conclusions, these samples contain very unusual alloying elements which are not present in aluminum alloys in 1947. If the samples are from an aircraft of that era, they're very unusual on that basis. And the coatings on the samples are very unusual because conformal coatings of this type were probably not available in 1947. The coatings are also somewhat similar to coatings on implants removed from people claiming alien contact. And the carbon nanotube indications are really intriguing. And if true, there might be smart materials which contain carbon nanotube electronics or to strengthen the material. Since the mechanical strength of the samples was not unusual, they should be tested for unusual electrical characteristics. I suspect they would show very unusual electrical characteristics. And the isotopic ratios of the elements in sample W1 that were able to be tested for, as I say, were very, very skewed and consistent with coming from a very far away extraterrestrial source or being exposed to a high flux of nucleonic particles at some point. Either way, it's very, very unusual. And they're reminiscent of isotopic ratios also obtained from alien implants and from an alleged piece of the Roswell crash debris, which was analyzed by the late Dr. Russell Vernon Clark. Dr. Vernon Clark analyzed a piece of the silicon sample that Dr. Lear had that I mentioned, and apparently had some sort of problem with the government afterwards and disappeared. I don't know whether he is still alive or what the deal is, but it was very, very, very strange. Dr. Lear said he just stopped answering his phone and nobody knew what happened to him. But anyway, the report is in the back of. I included the report as an appendix in this report if people want to read it. The results of the pendulum test indicate that the sample samples may still be emitting some sort of energy, and we should test for something like that. And further microscopic testing should be done on these materials to determine their internal structures, like I was saying, more testing like with fast atom etching followed by EDX mapping, perhaps, and micro resistance measurements. I think at this point I'd like to open up the talk for questions if anybody has any questions.
Awesome. Well, Steve, let me thank you. And in fact, I'm going to bring the guys back in here. I'll bring everybody back in, and I'll take that down. So, Stephen Colbern, thank you, sir. We're going to put our hands together and give you an enormous applause.
Oh, thank you. Thank you.
Yeah, it's a lot to go through, but Steve, I am truly incredibly appreciative for you running us through that. So for folks who don't know, and I just became familiar with your work myself. Like Jared Yates got me excited about what you're doing. You have been doing sample analysis on implants, the St. Augustine wreckage, orb samples, and all other stuff. And this goes back years and years and years, and very detailed analysis. So
yeah, I've been into this since 2008 when I started having alien contact of my own, or at least was convinced at that point by the evidence that that was occurring. I wouldn't even entertain a lot of this stuff if it weren't for the fact that I've got proof. But
well, it's detailed and rigorous. That's what I love about your work. You know, when I started going through the PDFs, it's incredibly detailed, rigorous, scientifically valid research, right? And that's like when you get into things like UFO reverse engineering and analysis in these areas, there's such this wide variety, right? And your work is just top notch. And so when I was reading through that PDF, I was just like, oh my God, this is amazing, you know? So now, Jared, did you have any questions for Steve?
I just am such a big fan because the amount of data that you have, Steve, in all of your different reports and all the different samples. Right now, I'm trying to take all of the information that exists publicly out there on UFO samples and make a meta study from them. And the information that you have, the papers that you have, the tests that you've run, second to none as far as just the sheer amount of volume of data in those. That we have not just what elements are present, but we got like isotopic ratios in these things. We got the microstructures in these. Like, if you wanted to make a meta study of stuff, like yours is at the very, very top of the list and where to start.
The thing that gets me about the isotopic ratio data is that it's pretty consistent in that the heavier isotopes are always overrepresented, and that makes it a lot more likely that it's not some sort of artifact or mistake or anything like that. I mean,
and that was something that you and I had discussed previously, was how one way that you could have heavier isotopes would be if it came from somewhere else.
Yeah.
But another way is if it just happens to have lived in a super radioactive environment for a really, really long time.
That is definitely a possibility, yeah.
And a lot of UFOs end up having radiation associated to them. Like when they land, that landing site's radioactive for a couple of days. And that's like a super common observed thing.
Well, and you know, that goes to another thing, and the Art's Parts is another example that people have said, you know, if these isotopic ratios are off, maybe that means that it was like near a nuclear reactor. Okay, how often does that happen in regular life, right? So in my mind, that takes it back towards not being, you know, a prosaic explanation.
Yeah, it'd have to be inside the core of the reactor, not just near the outside of the shielding or something to get like this.
Yeah,
I mean, for a long time too.
Yeah, is that something that we don't see that normally? We don't see, like, you know, hot radioactive core materials floating around. So,
and if that happened too, a problem with that theory is if that happened, they'd be radioactive, and these samples are not radioactive. There's a lot of radioactive isotopes that would be created too, and these are just the stable isotopes. So if that were the case, then that sample would have to be sitting around for like 10 half-lives of the radioactive isotopes or something to make sure that it was not radioactive enough to notice. And these are definitely background. There's very little if any radioactivity to them.
And if you take just the isotopes, just one element out of these things, you're not taking the whole picture into account. So all these microstructures in there combined with the heavier isotopes in there, when you take things together, it starts building a better picture of the fact that you're dealing with something that's highly anomalous.
Yeah.
Yeah. Well, and the meta study idea, and Jared, I'm incredibly excited about what you're doing there, because another thing is, I don't know, with you get into the error report, right, and it becomes this he said she said, but at least you're able to push that back one step at a time. With Art's parts, they're like, okay, this is prosaic, there's this is slag, it comes from this or that. By doing a meta-analysis, you're able to look at a variety of samples. And you know what? Maybe some of those are prosaic, but the overall pattern will probably show anomalies, right? That's the hope.
So far, all we have is null results, right? All the professional reports out there, they're all saying, yeah, it's all null results. Well, if you can start getting non-null results like Steve has, and you can start building a report of, okay, if you do find something anomalous, these are the type of anomalies that you should probably be seeing based upon the existing data already, right? None of the other official reports are really like bouncing off of known knowns. They're all going off of unknowns, right?
Yeah, absolutely.
One thing I've noticed about a lot of scientists is that even if they encounter something that's kind of anomalous, they don't want to say so. They want to like sweep it under the rug. I'm not sure why that is. Maybe they're scared of their funding being cut or something. But
something that I've seen is the noise floor, right? And in any experiment, you've got noise, you've got data that you're kind of throwing out, but then one of the questions becomes, what is the threshold for noise? And that, especially when you get into sample analysis like this, that makes sense. It's like science tends to confirm what it's looking for. And I think that's something we have to be careful about as well in our community, right? If we're looking at these samples, we have to be careful. Are we confirming only anomalous stuff while leaving out things that might be prosaic? But certainly, like with the Arrow report, I mean, we've done analysis on Art's parts. They, maybe intentionally, they left out parts that were anomalous there. So,
yeah, I think that usually people tend to err on the side of leaving out anomalous things rather than including them. For what I've seen so far, anyway. But there've been a lot of things in a lot of fields in science that have been swept under the rug that should have been investigated.
Well, guys, do you want to, let me see, we're getting close to the bottom of the hour. And so, Steve, let's do this. Let's put our hands together one more time and give tremendous applause to Mr. Steve Colbern. Steve, I hope to have you back on in the future to talk more about these and other samples as well. So, okay, well, I want to go back to Harry. Harry texted me and said he's ready to do the demo. Harry, are you all set?
I'm all set.
Okay. Well, and yeah, I'm awesome. I'm excited that you made it through the technical issues. Let me see.
What I did was I went back and just took all the RF stuff off, and I just made it regular where I can control the RPM speed of each motor. It's not remote controlled anymore, but that's okay. If you guys have been watching, it's sat here the entire time. It hasn't moved, which means there's no energy causing it to go this way or that way. It's just completely stationary. Now we're going to turn it on.
Is that a permanent magnet motor? Wow.
You can see it's not only moving, it's accelerating.
Is it getting cold?
What happens if you turn one of them off?
Now you'll see it'll unwind, giving back the energy that it just put into the torsion wire. So now you see it will unwind.
Yeah, again,
Move
Harry, that's
back and move
absolutely
back,
amazing.
all the energy we just put into it. You see how it's starting to slow down now? And it'll start going the other way. There we go. There, see how it's stopped now? It's not making any forward movement now. Now it's going to start going this direction because it's unwinding the string. We're only producing about 150, maybe 200 millinewtons of thrust, so it's not enough to go against the torsion line. But as you see now, it's starting to go back the other way. It's a very slow process. You got to be patient.
Yeah, well, no, but what you're doing is, again, proof of inertial propulsion, which is really amazing.
Yeah, this is absolute proof. And I'll run it again, and I'll get real close to the magnet array, and you'll see how the magnet is not slammed back in, how it's held in equilibrium until it comes around and then thrown out again.
Okay.
But as you see, it's moving back now. It's going back to its original position. But
and again, I do want to come down to Tampa and get some film footage.
West.
And you know, Drew is down in Orlando, so.
See how it doesn't get slammed back in? It stays all the way around until it's thrown out again. Okay. Do you see the orbit of the rotor magnet?
Yep.
That shows that it's not being slammed back in. It just stays in equilibrium until it comes around and then it's thrown out. So we're sort of getting a punch in one direction, but nothing back.
Yeah, so it's kind of floating. The magnet's kind of floating until it gets thrown out.
Correct. It's in equilibrium between the opposing magnetic field and centripetal force throwing it out.
Yeah.
And to get back to some of the things,
I know I opened up a container of sprinkled cheese.
one on one end and one on the other. If you go look at some of my videos, I've hung it vertically so that they're exactly on the same plane, and it still works.
Well, and then the videos that we saw, the ones that are on your website, and again, I dropped links in there. Those show that when you put it on a flat surface, right? So there's no twisting going on. It moves linearly. So
yeah, in fact, guys, I can run one motor faster than the other, and I can direct it. I can make it move. Yeah, this is it, guys. This is propellantless propulsion. It can go anywhere. This could fit right inside the space station. Right now, we're producing enough thrust to keep the space station in orbit. I did the calculations with an AI, and we need 3 of these at certain parts in the space station, and it would keep it up there indefinitely.
oh, there you go. There you go. Yeah, absolutely
As you
amazing.
see, it's dead stop. There's no energy in it. It's not trying to go anywhere. I think I've proven it.
Yeah, no, Harry, I am so excited. And again, my hope is to come down to Tampa. If you're open to it, I would love to come down. Key West, okay.
I live in Key West, Tim. Key West. Come down to Key West. We'll go in a boat. I'll teach you how to fish.
There you go.
All right, guys. Any questions?
Well, you know what? Let me bring the guys back in here. Okay.
Is that a permanent magnet motor, or how does it, or is it driven?
Oh,
Yeah.
this is just a little electric motor. Yes.
Okay.
Well, before anything else, guys, let's put our hands together for Harry Sprain. Harry, thank you so much. And you know what? Thank you for bearing with us. You're working through technical issues, and that's always super stressful when we're live. But
I plan. You always plan for something possibly to go wrong. So I had this available waiting, and I'm so glad I did.
yeah. No, you know what? It's so exciting to see this. And again,
Right.
so Key West, that is on my travel list.
Yeah. Come on down, man.
Yeah. So yeah, really, really exciting stuff.
All right,
Okay,
guys.
well-
So this is propellantless propulsion. It's called CID, Centrifugal Impulse Drive. It can replace ion drives, Hall thrusters, actually any type of small constant thrust. It can do the job.
Yeah. Well, did you guys have any questions?
Yeah, I do. I have.
Oh,
Yeah.
yeah. Mikolaj, go
So
for it.
we
And
were
I'll bring-
discussing that previously, Harry, but my point is, could you make these assemblies, put on the other side, one assembly on one side and the other assembly on the other side of the beam, and
Yes.
basically rotate them and
Yes.
switch the rotation and switch them again and stuff, and see if you're getting basically consistent results?
Yes.
Have you done that?
Yes. And it's also been tested on the water table at Georgia Tech.
Okay.
Yeah, we've tested it every way you can think of, guys. We've hung it upside down. We did this. We just everything.
Yeah. You know what? Let me bring Drew back in. Okay, Drew, I'm sorry about that.
Hi. I'm still, I don't get it. When you throw the magnet out,
Right.
so when it gets to the point where it throws the magnet out,
Right here.
you're-
Right.
is that where you're stealing some momentum?
Yes.
Okay.
Yes.
So if you're stealing momentum, you're reacting against the center of rotation of the spinny thing.
Correct.
Okay. When you throw the magnet back in, yeah, whatever. You push the magnet back in.
That's where you're wrong. The magnet does not get slammed back in. It's
I didn't say
held
that.
in equilibrium between the centrifugal force and the opposing magnetic field. It holds it in that equilibrium until it comes around and thrown out again.
Okay, so if
So
it
it
throws
only
it out,
has
at some point it's got to push it back in.
Nope, it holds it in equilibrium between centrifugal force and the opposing magnetic field.
Sure.
It's never
Does
slammed
it
back.
physically move?
Yes.
Okay. If it moves out, at some point it has to move back in order to be pushed back out again.
It does, but it doesn't get slammed in.
Okay. Ignore the word slammed. My bad. At some point, you're letting that thing come out, getting momentum
And it
from
doesn't go all the way back in.
whatever. When it goes back in at all, how come you're not getting the opposite momentum from that action?
Okay, you're doing what the physicists were talking about in that NASA chat site they blocked me from because they think they know frickin' everything. He's trying to say that as
Dude, I've been an engineer for 38 years. I don't know everything, but I know an awful lot about things that spin. I'm just asking you a direct question.
NASA flight website. Anyway, when the rotor arm is thrown out, it creates a little punch in this direction. The whole machine does not move back 20 millimeters. Because it happens so fast, punch, but no recoil, no bam back, no machine moving backwards. It happens just this direction, and then it's held in equilibrium. It never gets slammed back in. It never goes back in all the way. It's held in equilibrium all the way around till it's thrown out again. So
okay, that's wonderful. The timing is not important. If something goes out and you're gaining momentum from that action, however long or short it takes, and then something goes back in so that it can be reset to happen again,
it's not going back in.
So this
the opposing magnetic field. It holds it in equilibrium. It is never slammed back in.
what he's saying is
I'm going to
the
take
motion.
all this to mean that you're not going to answer the question.
The motion out is different than the motion back in, and again,
I get it.
This goes to the Jeffermenko jerk reaction. That was what he talked about. When Jeffermenko, his experiments involved a spark gap, and when he had a spark that crossed that gap rapidly, right? It was a transient spark. He recorded and documented. He said that there's a net directional thrust, and it was almost the same thing. So it is the jerk motion itself in one direction that's not reciprocated, right? So if it slammed,
all happening internal, so we're not violating any laws of thermodynamics. It's just something different.
Yeah,
everything is happening right here.
And that could explain why the net thrust is millinewtons, even though you've got heavy-duty stuff rotating. Because
it's actually the force on these is almost 9 newtons of thrust, but it's coming out for only a few milliseconds, just a pop. So I'm only getting just a few millinewtons from it, each one, about 25 millinewtons from each one. And then as they come out synchronously, pop, 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 it's just thrust in one direction.
Yeah.
The rotor arm is not thrown back in.
So again, to go back to the Jeffermenko thing, and this would go to what Drew was saying, the majority of the thrust is conserved, right? So the majority of this thrust, that 9 newtons, the majority of that 9 newtons is just dissipated. It goes out, it comes back in, you lose it. But this jerk effect, which is a small proportion of thrust,
constant, and you can watch it on the torsion balance. He'll stop to juke forward, and then all of a sudden it'll get smoother and smoother, and then it's just continuous.
Yeah. And so that, for me, that's really exciting because there have been other inertial propulsion devices that are similar. Now, one of the problems with those, and Harry has overcome this, is most of those shake themselves apart. Right?
I watched them.
Yeah, they literally self-destruct because
they try to go one way and back and forth, trying to get a little bit more on one side than the other.
Yeah. Okay, well, guys, again, super exciting. Does anybody have any more questions?
So there's a piston in there that's thrown out and hits the end of the travel and creates a thrust. Then the magnetic field pushes it back in when it spins back around. Is that it?
doesn't push it back in. Centrifugal force is trying to throw that arm out.
Right.
Okay, trying to throw that arm out. But the opposing magnetic field is holding it in.
Right.
So it never gets extended all the way, never gets pushed in all the way. It's about 50%. Stays there all the way around till it's thrown out.
Yeah, so it's floating, and then in one part of the rotation where there are no opposing magnets,
Yes.
it's able to extend further.
Yes.
And then it gently pushes it back in, and it floats again. So
right,
for the
sort
majority
of reloads it, but doesn't slam it in. There's no opposite reaction.
Because it's being pushed in by the magnetic, pushed in part of the way by the magnetic field rather than some physical object, right?
Yes.
So, yeah, I think I understand it, but that would be it's very interesting.
Yeah.
Yes. I think what Jared pointed out about it being something using the Mach effect principle potentially is a good point, Jared. That being said, I'm curious, have you done this experiment where all that is covered, isolated in the air?
Oh, yes. Yeah, I did it right here. It covered in plastic.
Okay.
I got a feeling that you're trading the compression of the wood. It's much like a seesaw swing. That's my guess. But I hope I'm wrong. But I think you're trading the compression of the wood for this tiny little bit of impulse in one vector direction.
Yeah, and that I mean, you're talking about.
I think that's what's happening.
Effects where it's.
But I hope I'm wrong because it looks really cool.
One question. Could this be a Coriolis force?
Affecting with the Earth's magnetic field?
No, the Coriolis force has to do with the rotation of the Earth. So in the northern hemisphere, this Coriolis force would rotate one way, and if somebody in the southern hemisphere, like in Australia, did the same experiment, it would rotate the opposite direction.
Well, on the Coriolis force might be present on the torsion balance, but again, this moves linearly on a surface, and on the water table, it moved linearly. So,
right.
So the torsion balance is really something he just rigged up, right, so that it's not as constrained. But
yeah, I just wanted to show it because it's such a tiny amount of force. It doesn't like move fly across the room or anything. You know, it barely moves, but a torsion balance shows that movement.
Yeah.
So the thrust is in the direction of the open part of those arcs away
Correct.
from you?
Correct.
Okay. So again, I'll suggest that, because it feels like we're in a inertial frame of reference, but we're not. Okay. So you get something moving fast enough. That's just a potential you want to, like I said, it's the way to do it is to do the experiment with the same symmetry in the southern hemisphere, and if it goes the opposite direction, then it's likely a Coriolis force. I'm not sure. The other thing you could do is you could model it, and that would tell you as well.
Well, it would not be Curtis. I could tell you it would not. I could 100% guarantee you it's not Coriolis, because number one, the rotators are counter-rotating.
Yeah.
And it moves linearly. So Coriolis might affect torsion balance. It won't affect flat table linear motion.
Right.
So, Coriolis, that would affect rotation. Now, if you had something on a torsion balance and you were shaking it and you saw rotation like that, even if you had complete conservation, then I would say, yeah, Coriolis, that would make sense. But again, what Harry's rigged up here is just kind of a demo of something that moves linearly. If he sets that on the floor like on a skateboard, it'll go forward or backward, or on a water table, right? We saw the water table video where it goes forward.
Yeah.
So.
Yeah. It only moves in one direction. We've tested it on the water table. We've tested it on glass. We've tested it on an incline, on the pendulum. We've run every single test you can run.
Right. So on the water table, was it vibration isolated?
Yes. And look at go to our website. You can see the report on it from Georgia Tech.
I see.
They used high-speed cameras, all this other stuff. They used all this math and all these equipment to any movement, and it was completely isolated. They had it down in the basement somewhere.
And well, in terms of like the isolation between the device and the water, that's what I mean by isolation dampened. So the device itself, that piece of wood, is probably vibrating, right, with the motion. Mm-hmm. So that's kind of the question.
Yeah, they took this and they put it on a big styrofoam thing and floated it in a pool about this size, actually.
I see.
And they put it in the center and let it stop and everything. And then we all left the room and we waited, and they remote control turned it on, and it moved, and it produced 710 millinewtons of thrust.
It'd be interesting if you could levitate it with a balloon and get it to neutral buoyancy in the air.
Yeah, that would be interesting to see if I can get it to fly around.
Although with the balloon,
the main thing that proved it to me 4 years ago was the pendulum test. I would do it on the pendulum, and it would move to one side and stay.
Deflection, yeah.
And that
pendulum
was
deflection.
And once Professor Mitchell Walker saw that, that's when he said, "Okay, bring it down." You know, it took me 4 years working with Professor Mitchell Walker. I proposed the idea to him, and he said, "Great, but eh." So I went back to him and I said, "Hey, let me build a prototype of it." And he said, "Sure, build a prototype." So I built it, I brought it back to him, and he said, "No, it does this and it does this, and it has first energy and second energy and blah, blah, blah." So then we go and I built another one with the changes that he had suggested, brought it back to him. He tried it again, not quite right. This went back and forth for 4 years and 9 iterations of CID, back and forth, until finally I brought him one, and he said, "Wow, this is showing something. Let's put it on the water table." So we put it on the water table, but it was only one ring back then. So it did what you thought. Outside would turn one way and the inside would turn the other. We couldn't find a thrust vector. It was just sort of all over the place. So then we decided, okay, we've got to have 2 counter-rotating ones to stop that counter-rotative force. So we built this new device, CID, and we brought that back to Georgia Tech, and they tested it on the water table. And this is the one that produced roughly 710 millinewtons of thrust, about 235 RPM. It did everything it was supposed to do. We then took it to Orlando to the Spacecom show, and we demonstrated it live on the torsion balance, just like this, in front of everyone. And they were just amazed. I've tried it every way I can try it, guys. I've held it this way, like vertically, so that one CID's here, one CID's here, and it still moves. And the video's on the net, you can see it. I turned it upside down. In my other videos where I have just one ring, if you go and steady them, I can point the thrust up and it will go up. I can point the thrust this way and it will go that way. I can point the thrust down and it will go down. Absolute proof that we're producing a thrust that I can direct.
One thing I think it'd be interesting to try is to put some kind of light material behind it in the opposite direction of the thrust, suspended from a string perhaps, and see if there's any reaction on it. I could be wrong, but I think that maybe it's creating an impulse to the ether behind the device, and you might have a flow of ether going the other direction.
I have
that would be interesting. You know, one thing
on all that, I really have no idea. I have put this through the AI, Julius, one of the best physics AI program there is, and I pay $80 a month to get the top of the line, whatever. And I have proposed this to that physics chat site over and over and over in so many different ways. where I build it individually, each magnet. I build the rotor, I build everything. And the results are always the same. We're producing thrust.
Well, that shouldn't work according to the classic laws of physics. This is proof that there is an ether, if you ask me.
The AI agrees with you.
Now, Harry, let me ask about sound isolation. And I know that with a prototype like this, I know that's not a primary goal, right? Like the primary goal is get it working, get it producing thrust.
Right.
But one thing I'd wondered about is, have you ever thought of putting like maybe a little rubber washer on the shaft for the magnets in the center? Something to just give it just
try to dampen it to get that force more smoothly, smoother, instead of a wham, 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 wham. Yeah, there's a lot of things that we're going to be doing.
Yeah, I was just curious. And then the other thing I kind of wondered about was, it looks like you have 4, and again, it's getting it working in, initially. It looks like you have 4 rotators in the center.
Yes.
Have you thought
on each one, so 8 magnets total. And this can go bigger. I've been doing designs where it's about this big, and I have 16 magnets. And they're all punching out one after the other.
And so you'd still have a clicking noise, but that would smooth it out. And if you were able to do a little bit of audio isolation there,
right. And
you
the
might
other thing I was thinking is I could put the whole thing inside a vacuum sealed container, and you'll never hear it.
Oh, that's a good point. Yeah.
And it wouldn't have to be a hard vacuum.
Yeah, Curtis, go for it.
Yeah. So about that, one thing about the I don't know, Harry, are you familiar with the Woodward's Mach effect drive?
No.
Okay. So yeah, we have a lot to talk about. So one of the things that happened with that was that initially Jim Woodward, he was doing the experiment in the vacuum, and they convinced themselves that it didn't matter if it wasn't there. They did some steps and said, okay, we can take it out. And one of the reasons they wanted to take it out is in the vacuum it was on a torsion balance, nonlinear equilibrium, and so people weren't convinced that there was some kind of nonlinear dynamics going on. So wanted to take it out of the vacuum, put it on a pendulum type device, 3 pendulums, like I said earlier, with 3 lines from the ceiling, about 2 meters long, a really good setup. The problem was it was in air, and so as they went on with that, they started optimizing the force, changing designs, tweaking things. And when I joined the project, I was really concerned because it looked to me like it was basically pushing air. It was making, millinewtons, and it's a small device. Okay. And what ended up happening is Jim finally put some baffles, and basically the thrust kind of went away. We did a COMSOL multiphysics simulation, and we showed that at resonance, we were getting up to a Newton of force from the air. Okay. So now in terms of vacuum and how deep of a vacuum you need to go, you want to go below a millitorr. You want to be well below a millitorr. Millitorr sounds good, but if you look at the helicopter on Mars, right, you still get vorticity, you still get a lot of stuff. So you want to be in the domain where there's basically molecules aren't bouncing off each other, right? They're bouncing off the walls, and you're not able to push off the air very
quickly. What we want to do to just prove it and get it done is I want to take it to the ISS. I want to build a small model, maybe a little bit smaller than this, have an astronaut bring it right up to the ISS in a suitcase, hold it up in microgravity, turn it on, watch it fly across the ISS.
Well, if only we knew somebody with a large vacuum chamber.
Yeah, I'd be happy to put that thing in a vacuum chamber. And I've got a vacuum chamber big enough to put that thing in and let it spin. But that's not the point. When you want to go to the ISS, they would love to have you, but it's a 10-year process.
No, you said that before, and I have to correct you. I'm already talking to people. I'm getting in there next year.
Okay, good luck.
Money.
Yeah.
The other half of my team has has about 8 projects headed for the moon. I'm telling you, it's a 10-year dream.
Yeah, heading to the moon, not a suitcase going to the ISS. Big difference.
And
Yeah, I would certainly put that in the vacuum because, like I said, the air effects can be vastly underrated. Even some vibration, you have some resonance, or I can hear it. I can hear the sounds.
But if he's isolated it, he's atmospherically isolated it in the past.
Yeah, I've
with
already
enclosure.
tested it with a cover on it. There's no difference.
Yeah, the cover is a good step, but you definitely want to put it in a large vacuum.
Room. The air's off, everything's off. There's absolutely no wind in this room. You can tell the torsion balance hasn't moved at all.
Yeah, no, there was it was the same kind of thing. It was really hard to diagnose with Jim's setup. It was the same kind of thing. But I'm not saying that's what's happening there, but I would say definitely.
No, I appreciate all
take Drew's.
I check everything, every single thing. I do it 20 times if it over and over and over and over, and the results have always been the same.
Right.
Yeah.
Understood. Yeah. I would suggest take Drew's offer. He has a rather large chamber. Look at the size of it and put it in there. Do something like that because, like I said, there was a big issue because we
would go with Mitchell Walker at the Daniel Guggenheim Aerospace School. They've got an $11 million vacuum chamber.
Okay, there you go.
Yeah.
Definitely do that before you go to space. The other thing I would say in terms of the theory.
Wait. Why? Why do I have to go in a vacuum chamber if the astronauts are bringing it up inside the atmosphere, inside regular atmosphere, nothing, no space, no vacuum, nothing, and they're just going to keep it there? So what's the point of the vacuum chamber?
Oh, that's to eliminate that it could be an air effect, right? That's what the vacuum chamber does. So.
No.
I think Harry's talking about just cutting out the middleman, basically.
So hold on a second. So if it is an air effect, all you're going to do, you're not going to have a net force in the ISS. So that's what was happening with our experiment. I'm not saying it's happening with yours, but that's definitely something you want to address. Like you've put it in a vacuum, and it's not the air pushing. And the thing about air is not okay. It's not you're not doing an ionization. We weren't doing that either. And it's not like a propeller. But what we were doing which was not expected, was that vibration was actually at a certain resonance, was actually pushing one side more than the other somehow.
Okay.
Now, when you have a system, which yours has a little bit of an asymmetry, the thing about fluids like air, it's really hard to calculate, right? So even if we did a multi-physics simulation, we happen to see it with the multi-physics simulator.
I did that a multi-physics simulation on it with COMSOL, and what it showed that even if there's a 5 RPM difference between them, it's micronewtons of thrust. If it was,
you had air around it.
It would take 30 minutes to move that far.
Yeah, and you had in COMSOL you had air around it.
Yeah. Well, guys.
Yeah.
And it's 4:00. We're just about at the top of the hour. So if it's okay, why don't we do this? Let's put our hands together and give Harry another applause. Harry, thank you so much. Thank you so much. And what I want to do now is, if it's okay, let's move on to lab time. I think, Curtis, you probably have updates, right? And then Drew, hopefully you have updates. Curtis, do you want to go?
Yeah, I want to.
Okay.
Before I start the update, I want to talk to Harry about theory for just a minute.
And then I think at some point Jared has a brief update on Art's parts too. So, but let me take everybody out and. Okay, and Curtis, there we go, sir.
Sure. Okay. I uploaded a presentation.
There we go. Okay.
There we go. So Jim was in the lab today, and one thing. This lab update is going to be pretty similar to the open mic in terms of where we are. But we have received, or we are about to receive, or we're getting them, I think they're in shipping right now, more stacks from another manufacturer with the 1 millimeter thick discs. And I'm excited about that because that allows us to test. We've been using eight stack discs that are 2 millimeters thick in the piezo stack that's center of the drive. We're replacing that with, we're getting some stacks that are 16. And what that allows us to do is actually have a higher power density so that DPDT is higher in the experiment. And so I'm really excited about that because that is supposed to get us basically approximately an order of magnitude more thrust. So if it's really the Mach effect, then we should immediately see a big improvement on the thrusters. So the other thing, we are still working on a linear experiment. So that those parts are in the works. They're being shipped. We're putting together this linear experiment where we're going to hang the device in a vacuum on a linear bearing. So like was mentioned earlier about having a water table type test, a linear test, that's important. I agree with that. But what we're going to be doing is having the device in a vacuum, in a tube. This is showing something that's like off the shelf. We're actually going to make a custom one as well. And we're going to bring it down to vacuum, monitor the vacuum, and have that whole device together, see if that can move. And of course, if that does, then we're going to take further steps. So we are trying to move away from the torsion balance, which has nonlinear effects potentially. Again, right now we're still on the bearing system. We have tried multiple configurations, and we even tried recently a configuration where we have just the supports on the brass side. They're not on the other side of the aluminum where there's a lot of motion. And we have done that experiment, and we still see that we're getting tens and hundreds of newtons and higher in terms of like that force. And again, we're using the sweep, right? So we're not on a constant frequency. So we're still seeing that happen as we go along in our calculations here. So that's something that, like I said, we have to make a linear experiment and try to get the potential of nonlinear dynamics causing the motion with the torsion balance, especially that balance is a nonlinear equilibrium, and so it calls into question what the real force is. But as you can see here, the device itself, it moves quite a bit. Even though there's a little bit of stick slip at the beginning, you can see they move together. So we're still getting the results that we have been getting previously. So that is the lab update. We can talk about theory, but I'd like to talk.
Yeah. Do you have more to? Yeah. Well, and Curtis, thank you for the update, man. That's awesome.
Sure.
Do you have? Here, I'll take myself back out. Go for it.
Oh, if you want to bring the rest of the guys, we could talk about theory. I think that would be good. I don't know if Harry's there. Okay, so Harry's there. So Harry, one of the things I wanted to ask is in terms of the Woodward effect, and I think if you want to get rid of the slides, we don't need those because that's more to do with overall theory. But you might want to look up the Mach effect, Harry, and we can talk outside of this, and I can put you in touch with Jim as well. So in Jim's theory, so basically what he has figured out, and there's in terms of like the theory side, there's no reason fundamentally why it's wrong. It's like has to be done by experiment, right? So in his theory side, he's basically taking the divergence of the matter field and basically showing that if you get a change in motion or change in energy really quickly, you're basically pushing against the gravitational potential. And so that's why the thing what you're describing, that jerk motion, that's intrinsic to this, right? Because the higher that is, that's the higher derivatives. That really plays into the Mach effect. So it's your device is a variant of the Mach effect experiment we're doing. There's another one called the Mach-Lorentz thruster. That one's more electromagnetic in nature, but your experiment seems to be potentially like that. Now, that being said, like I said, we have had issues with air, so I would highly suggest that. But in terms of the theory side, you should be able to, using Jim's work, especially if you're working with other scientists, his equations are not that difficult. You should be able, and his papers are published, so you should be able to find those and work out for your system what the theoretical thrust is based on that. So
okay,
yeah,
will do. Thank you.
Yeah, like I said, you can reach out to me and Jim's still around, so we can talk about it. And the other thing about Jim is that he's been around, so he has seen pretty much everything. And he's been in this space, so he knows. He's a physicist, but his PhD work and his work at Cal State Fullerton was he's a professor of history.
Nice.
And so his specialty was basically a history of Einstein and all that stuff. So he's a historian as well. So he's been keeping track, and he knows all of these technologies over the years.
Right. Okay. Thank you very much.
Did Tim leave?
Yeah.
All right. So Jared.
Sorry, sorry about that. I thought I was in there. Okay. Do you think I could go to Drew now for a lab update? Or Drew, do you have a lab update for us? Oh,
I do. Can I do the end? I'm trying to clean up this graphic so it makes some sense.
Yeah, absolutely. Yeah. You know what? Let me go to Jared. I think Jared had an update on our parts. Jared, go for it, sir.
Yeah. Let me share here. Give me one more moment. Percent. Go. Slideshow. All right, y'all should be able to see that. So I've been obsessing recently over the colored dots, the bright dots on the arts part sample. I've been trying to be able to come up with at least a good enough argument on why I think they possess symmetries that are useful. So that's been most of my analysis recently. So first off, what the heck's a quasicrystal? A regular crystal? It's periodic, right? Quasicrystal, aperiodic. You can see shapes in there. You can see these lines in there. So there is some level of periodicity. There is some level of symmetries in there. But the ratio distances between these red dots has the golden ratio in it. That's like one of the hallmark features of quasicrystals is golden ratios all throughout the thing. Fibonacci sequences, golden ratios. Here is another picture of what a quasicrystal looks like. Once again, pretty symmetries. And you can see how different dots are different sizes. Part of the reason for that is because a quasicrystal is kind of like taking a shadow of a three-dimensional object projected down onto a 2D surface, right? So this would be kind of like the farther away parts of that 3D crystal structure being shadowed or projected down onto the flat surface. That's the whole gist of quasicrystals, is that they are higher dimensional objects being projected down to lower dimensional space. All right, so this is part of the issue that I've been having in doing our quasicrystal analysis on this. When I went and visited Mark in November to do more testing on the sample, we had it on the schedule to do more scanning electron microscopy, specifically on these spots and other spots on the sample, to be able to get way higher quality photos of all of these organized dots here. So unfortunately, we canceled that because the opportunity came up to do some isotopic analysis. And so that sample is currently undergoing some really long tests to be able to find out all the isotopes that are in there. And we already have some preliminary results on that, but we're going to hold off presenting those results until we're done with the much longer test that has a lot more info in it. Anyway, so these are cell phone shots that Mark took with his cell phone of the computer screen of the scanning electron microscopy stuff while it was going, which is why it's so stinking blurry and why you got some of these like lines on there. And yeah, so I've been doing the best with what I got. But I think here you can see we got like some straight line guys in there. Over here, we got like these two straight lines coming up and down. You got like this triangle over here. It seems like there's some lines on these things. So what I've done is I've taken this original one here and I have extracted just those dots, and I have associated the sizes here. See how that's big and white, little white, big and blue, little blue, right? I've kind of tried to extract the sizes and I've made them all round just to make this easier to analyze. First thing I did was I checked the sizes of those dots to see if there was any kind of regularity there. And there, if you follow this blue line there, that is a power law, which is indicative that there might be some level of order in there. But I mean, you got reflections coming off these things. You got, you know, blurry photo. There's 15 ways from Sunday. You can't rely on that alone. And there's this other thing called Voronoi tessellations, which are used for identifying quasicrystals. I have such a limited amount of experience with these, but the gist is that you're basically showing like the overall distances between all these dots relative to their other neighboring dots. And if it was quasicrystal, you should see some level of regularity in there. On the top here, I got for the dots on that first picture sample. And down here, here's just a random one GPT came up with to show the difference between the two. And I think they look kind of similar, but there are a couple of spots that draw my attention. That's like right around here where you're starting to see some regularity. And then right here, you're starting to, again, see some of this regularity that if you come over here and you look at these lines here, it seems like it, I don't know. Once again, not going to rely on the Voronoi. So then we go on the radiuses, right? If you start drawing circles on this, is there regularity to the distances away from a center position at which a lot of dots start falling on those circles of certain radii. And sure enough, if you look at these peaks here, we start seeing some level of regularity. I'm not going to rely on that. The most important thing that you need to do is you need to do fast Fourier transform. So here's a picture I took from a YouTube video where a guy's showing how to do this. Over here on the left, you can see he's got a picture of a quasicrystal going on. And then he's saying that normally with material science quasicrystals like this, you never get nice, pretty Fourier transform photos. They're always like rotated all over the place. So normally what you'll see is these rings of different radii showing up on your FFT. So here I downloaded some FFT, some image analysis software, and started doing some FFT. Down here, you can see this yellow square here is the area that I selected because we've got all that crummy noise on the edges and the corners of that image. But just from this red, you can kind of see those lines and dots a little easier, I think. Anyways, the X and Y axis bright lines you see here indicating, you know, the frequency at which it's taking a lot of readings. That's in part because you're just getting pixelation, right? It's a picture of a picture. So ignore those vertical and horizontal lines there. The more important thing is how we have kind of some of these darker rings in here, and they're very faint, and I've contrast enhanced this photo over here to make it more obvious. But it's super faint. I think it's there, but it's super duper faint. We are not at smoking gun. We are at barely a warm steaming barrel. So that's for this QC1 image. And then for the QC2 image that has those two vertical lines and the triangle thing over there, once again, I did some of this, this contrast enhancing of the original FFT. And once again, very, very faint, but I think it's there. Some things that kind of look like shells, some potential for some periodicity, which once again, not a smoking gun, but enough to make me convinced that it's worth continuing to pursue. And then I was able to pull this FFT image out of it. And this is where I started getting really excited. So you can kind of see we got some of these weird darker pockets in here. right? And if you look at the white area here, you're starting to get like this weird tower shape. So what I've done is I've kind of outlined that, make it a little easier for you to see that, yeah, there is some kind of geometry going on with those dots. And while we do have those rings, we also have some of these really weird additional shapes coming out on the outside highest order of those. So if they are quasicrystals, it's a really high order quasicrystal. So now I'm just going to kind of riff for a bit, and I'm going to take you down to the bottom of the Marianas Trench of the Kool-Aid rabbit hole. So hold on. So quasicrystals, it just so happens that prime numbers are described with this thing called the Riemann zeta function. It turns out that the aperiodic nature of those prime number zeros on the Riemann zeta function act like a quasicrystal. So that's cool. Quasicrystals and prime numbers have a relationship. What else has a relationship with quasicrystals or prime numbers? Turns out that the shells of the hydrogen atom seem to follow some similarity to prime numbers. Wait a minute. So the most fundamental atoms we got have some prime numbers built into them, and prime numbers just so happen to be related to quasicrystals. Okay, that's weird. What else is related to it? Oh, DNA happens to have prime numbers in it. You can use prime numbers to describe DNA. Well, that's getting really weird. So atoms and DNA and prime numbers all seem to have relationships to quasicrystals. What else has a relationship to quasicrystals? Oh, the microtubules thing from Penrose, that happens to seem to have some quasicrystal element playing a role in there. So consciousness, DNA, atoms, prime numbers, all related to quasicrystals. Oh, I'm losing my mind here with just how many things are related to quasicrystals. I'm seeing them stinking everywhere now. Anyways, so going back to actual engineering stuff. So I started tinkering around with making my own quasicrystals here. My goal is that if I can print out some of these and I can try to wire them up in such a way, I might be able to see if I can't play around with some of Drew's stuff. And if nothing else, I just want to see if the electric fields that you get off of a quasicrystal are like super non-uniform and like create all these overlapping hotspots, and maybe that's usable. I don't know. So I've done another one here. I think this one looks a lot better. It's got some really high density to it. Quasicrystals happen to have some of the highest packing density that you can get, which is also really interesting and useful a million ways from Sunday. If you want to read more, I got like a 27-page Google Doc of just all these different quasicrystal papers I've been collecting. If you want the link to this presentation, I made a tiny URL for it there. You can see UFO-QCS-presentation. Yeah.
Awesome, Jared.
For like hours.
Yeah, you know what? And I just forwarded you earlier today. I forwarded you an email from Clee Irwin, who was talking about quasicrystals being a three-dimensional representation of higher dimensional matrices. So,
yeah. So him and David Chester worked with Clee for a while there, and their work really inspired me in a lot of different ways. They showed that at this higher level of reality, this mathematical abstract level of reality, geometries of quasicrystals seem to coalesce to take shape to explain all of the fundamental particle interactions that we see. Garret Leesy's E8 model is another example of a quasicrystal interaction in that way. So yeah, if you can somehow tie, this is where like just marinate yourself in the Kool-Aid. If you can somehow tie the most fundamental abstract, like metaphysical level of reality of math into particles, into atoms, into DNA, into microtubules for consciousness, like that's amazing. And the fact that it all relies on the golden ratio, I mean, come on, eat your woo heart out here, man.
Yeah, well, there we go. But Jared, it's absolutely amazing. And you are working on a meta study, right? And, Steve Colbern has provided you with tons of data, and we're going to be looking at samples. So we've got a ton of stuff. It's just putting pieces together, right? So, Okay, well, let me see. I think that was it for. Oh, Drew. Drew has an update.
Okay. Yes. It's a slideshow. So
Okay.
if you want to,
Yeah.
Whatever.
Let me see. Is it analysis report on? No, that's.
No, I'm sorry. I was just going to run it on my screen.
Oh, okay. Yeah, go for it.
Yeah, I'll just run it on my screen. So, don't know. You want me to just go ahead and present?
Yeah. So just
Okay.
present and then share screen, and it'll ask you. You can do a tab or the entire screen or maximize or whatever. Okay, there we go.
Awesome. Okay. The update is the same pretty much as it was a month ago. It takes an insane amount of work to be able to run the simplest of tests. What I started out about 2 months ago was refurbing my old big vacuum chamber, and basically I had to get rid of all the stuff that was very dangerous, and I just replacing everything with turbos. So for example, this is just big stuff. I should have cut those flanges off, but my plasma cutter is on loan to a buddy. So I went ahead and had some flanges made up. Got some buds coming over tomorrow to TIG weld them in place. There's going to be 4 turbos in place of the 2 monster diff pumps that used to be on there. So the goal is to switch over and be able to pump this chamber down in about 12 hours. That's the dream. The littlest change requires an insane amount of work. So I had to clean up all the interfaces. I had to go create, like this is a CF 4.5 nipple that the 2 of them are going to get welded on. This used to be a mechanical pass-through, but it's just easier to switch over to electronics inside. So I'm bringing a 60-year-old vacuum chamber up to kind of today. Just to give you an idea of the scale of this thing. It weighs about 3 tons empty. And that thing is 72 inches in diameter on the outside, and it shrinks about 3/8 of an inch in diameter when it's under vacuum, maybe a little less than that, maybe a 1/4 of an inch in diameter. It's insane that thing shrinks and changes shape as much as it does. But anyhow, just more pictures of that, and I'm cleaning the shop up around it so we could work on it. Chamber, and this is what's going in it. Those are the 2 new portable test rigs. The clear looking thing right here. This is the ITO shield box, and each one of these is going to go in the small chamber, and one of these is going to go in the big chamber. And the feeds to the new setup is going to be a single USB cable. The goal is to just reduce the interfaces to the hardware, because it is unbelievable how easy it is to introduce a mistake that looks like thrust into the system. So I'm just going to leave it there. I spent the last 10 years removing things that were lying to me. And this, although it doesn't look all that exciting, is pretty cool if you're me and you finally got it to work. This is my P4 thruster. This section right here is P4 thruster making negative 430 micronewtons. This is the P3 thruster making about 380 micronewtons. And this is the P3 plus P4 thruster making negative 1050, which, I don't know. I came to the conclusion that the P3 and the P4 are both working at the same time, making more thrust than either P3 or P4 individually, which is big news in my world, because getting thrusters to play together nicely is very, very difficult. It has eluded me for a long time, but as of whenever this was, the 20th, which was, yesterday, it no longer eludes me. So I'm very excited. That's it. That's the end of Florida update.
Awesome. Drew, thank you. Thank you so much, man.
You're welcome.
Okay. Well, yeah. So I think that's it. So, you know what I'll do is, as promised, I'll drop that link. Let me find the link. I'll drop that in, and if we'll stick around and do open discussion for a little while. And let me find the link first. Sorry, I'm making noises today. I don't know why. Here we go. So we do have a limit, but I will drop this into open comments. So it's kind of first come, first served. And again, we try and keep this like internet appropriate, right? Because we have a diverse audience. So yeah, so I'll drop that link in there. So that's StreamYard. And, you know, we have a bunch of folks who are in chat who have been there. Some of them may not still be there, and they had some questions. So yeah, this is exciting. And we're like right there for Christmas. So that's why I'm living on caffeine, the green tea today.
Hey, Jared, did you ever figure out what all the little dots meant? I know you got all excited about it, and but did you figure it out?
So there's so many different ways that you can run with it. One way is with charge density waves. So got a whole charge, surface charge, free charge on the surfaces of all those dots. And then you put a punch of extra charge. And now you got this wave of extra charge going through the whole thing. That's a charge density wave. So it seems like that might be one way to utilize them. They create a whole bunch of cool nonlinearities with charge density waves. There's the hotspots, overlapping fields of hotspots that I've talked about. So because the Fibonacci sequence is in it, that means that you get all these nestings, right? You get like the maximal amount of scaling possible when you're invoking the golden ratio. So if that's the case, then it's creating really strong fields.
Going back to your hotspot thing, you said overlapping and it makes hotspots. Are magnetic fields like electrostatic fields? Do the lines ever cross?
That's a great question.
Because I know in electrostatics, the lines never cross. So if you got a whole bunch of stuff headed in the same general direction, like if stuff's coming in like this, whatever, if the stuff's coming in, it doesn't all just jumble up together and go that way. It always goes right next to each other. Doesn't matter how close they are, but they never cross. One field might push the other field out of the way, but the fields never overlap and add up. Then there's no nodes of high intensity in electrostatic fields. There's nodes of no field, but there's no nodes of high field.
So let's do a thought experiment for a second. If you had a square and each corner of the square was a dot, right? And you charged all those up and you had another dot dead center in that square, right? What you're saying is you'll get in between, any dots, all the fields will go that way, but you won't get these fields coming over the center dot, right? Well, what if that center dot was a different polarity? What if it was the opposite polarity? Then what? Then
everything would go in towards it.
It would all suck in, right? And so then you have those lines coming together.
Well, yeah, now you have a source sink, but if they're all the same, if they're all sources, there's no overlap. So if one's a source and one's a sink, yeah, the lines, the field lines go in. If you got a whole bunch of sources and one sink, then boom, everything comes down, and that acts like a node, if you will, like a concentration, because that's where everybody wants to go. It's the hot spot, it's like Club 21 or whatever it is.
Yeah, and with quasi-crystal lattices, I'm not sure how that would all work, because every single dot is gonna want to act like its own node, right? Because there's bajillions of symmetries overlapping with each other. So I don't know if there's any way that you could
But they're all on the same surface, and the surface itself is charged. So they're all going to be at the same. They're all going to be on the same. They're all going to be positives. They're all going to be negatives. So they're all going to be. Let's say they have a little third dimension to them. They're a little height of some sort. Because if they're all flat, doesn't matter what they do. Nothing's ever going to just a big sheet of nothing. If they're little bumps, then they're emitting a field array. They're emitting field lines coming off of them and stuff. But they're gonna obey the same rules. No two field lines can cross each other. So they're going to be nodes. They're going to be zones of less field, and there's going to be areas where all the field is bunched up, pushing on each other. But nowhere is there going to be a great big compilation of field. I don't think so.
If that's the case, then if having an arrangement like that would cause all these bunchings of all these different lines, I wonder then if you were to take the reciprocal of that, right? The inverse of that, where you're looking at all the dead spots, right? Instead of hot spots, maybe it's the dead spots that are the important part. Because all those lines are going to end up canceling out, or not canceling, but like pushing out in the in-between spots between all those dots. Well, if you take all the dots away and you just look at the geometry of those bunched field lines, you'll probably once again come up with a QC-esque type geometry of those lines.
Yeah. I think it's going to turn out to be far more important in like a diverging electric field or a diverging magnetic field. And we're going to start getting into the physics of divergence, field divergence. Because that's where I've spent a lot of my time lately. We've kind of gone away from electrostatic pressure, which works fine, but the divergence force is, I don't know, something on the order of 1800x stronger. So you always want to play with the more bang for the buck, and the divergence it's a little trickier to get thrust out of it. So it's a lot trickier, but the rewards are insane. You even have to you can even pay the penalty because the thrust is in opposite directions. So you just generate all of the electrostatic pressure force and throw it all away because the divergence force is coming in right behind it in the other direction, wiping it out and still overpowering everything. So that's where those microdot things might come in handy, or whatever they are, the little dotty things. They might just be able to direct the diverging fields in some really clever fashion. I'm sure these little alien dudes are smart. But is the guy who had the Roswell, the pre-Roswell stuff, is he still here?
Steve, yeah.
Yeah, Steve is here.
Oh,
yeah.
Okay. There were crashes before the Roswell 47 crash?
Oh, Steve, you're muted, sir. There we go.
Opinions vary on the exact date, but it was supposed to be at least several days before the Roswell crash. And there were crashes before that too. Apparently, rumor has it that Hitler's guys got a hold of a crash saucer back in 1932 in the Black Forest, and they tried to reverse engineer it and found out that it was powered by some sort of anti-gravity drive, and that they communicated telepathically, and they reportedly got some of the best psychics in Germany to try to communicate with them and succeeded. That's the rumor anyway.
Okay.
So yeah, there were crashes.
Are these little aliens just really bad pilots? I mean, they're running into forests, and they come all over across the universe to crash.
That's a very good question. But if to do what they're doing, what they're apparently doing in this hybridization program, and their program to mine the Earth and the Earth-Moon system and such, they must be doing thousands of sorties a day. So it's inevitable they'd have some accidents. And they in 1947, again, rumor has it that they ran afoul of some very powerful radar systems that existed in the White Sands, New Mexico area. Very powerful radar apparently interferes with their drive, or at least with the older ones. Corso said that in his book, The Day After Roswell. He said that the only way they could shoot them down is by training a very powerful radar on one, and that would partially disable their drive. Then they might be able to hit it with a missile. So that's probably what happened to them in 47. Either that or they were hit by lightning. Nobody knows for sure.
And it's worth mentioning that there's only been 3 instances of like natural quasicrystals showing up. That's in a meteorite, that's at the Trinity test site from the nuke blasts, and then there was another instance where like a power pole exploded in some sand, and it ended up creating quasicrystals in those sand grains. And so if indeed our piece came from a saucer that got either hit by lightning or hit by some kind of directed energy weapon, either one, those ruptured little microspheres they're creating, those bright dots just so happen to be arranged in a QC lattice. It might be that that's just the imprint that the fields put on there, right? It's just those are the little capacitors that happen to blow because, you know, quasicrystals plus fast discharge type thing.
Yeah, and going to the UFO thing, kind of what Drew was digging into what Drew said a little bit more. These sightings, you know, you have a few big ones, right? Like Kecksburg was one example, and there was the Rendlesham Forest, you know, in the UK. That wasn't a crash, but that was an encounter. Then Roswell, everybody knows about that one, right? But what's interesting is when I dug into this, I mean, obviously there are thousands of sightings with some veracity out there, but there are also some really big ones that predate, you know, like there were a bunch of sightings over Hanford before Roswell, going back to 1945, 1944. Again, it's that nuclear connection, right? The one that nobody really understands, but there's something there.
Yet another reason why the meta study is important, because if we can identify correlations, not just with the elements, but with the structures, the microstructures they're using, we might be able to come up with a better idea on what kinds of technologies to pursue to improve upon in order to maybe replicate some of their effects. One other thing I'll mention is that if indeed what people are claiming that the craft themselves are conscious or AI or whatever they are, and it just so happens that quasicrystals, QCs, are really good at explaining the microtubule consciousness connection thing, then once again, just riffing, it might be possible that these QCs we're seeing there have nothing to do with the fields. It's actually the computing system that is it's simulating a consciousness, right? It's simulating a mind, because we already know that our minds are working using these kinds of structures. So why not make a computer use the same thing? And if you can put that computer in your craft and utilize as much surface area of your craft as possible for computation power, like, you're going to have a really smart craft.
Yeah, I suspect that all of these alien materials have the equivalent of supercomputers built right into the metal. The carbon nanotube electronics would make them make the electronics smaller than our silicon-based electronics, and also much more robust.
Yeah, and one of the things that I think that the quasicrystal, not just quasicrystals per se, right? Because Jared, you were talking the other day about some of these patterns are like quasicrystals but don't fit the parameters of that, right?
Overlapping quasicrystals at differing symmetries. So quasicrystals come in a handful of specific symmetries: 5-fold, 8-fold, 10-fold, 12-fold, right? Well, if it just so happens that we see a 20-fold symmetry on our sample, then it might actually not be a 20-fold symmetry. It might be an 8-fold and a 12-fold overlapping over each other. Well, if you start doing differing symmetries like that, and you have those kinds of things interacting with each other, the modulation that's going to occur from that, holy crap, dude, like, super complex. Just one symmetry type alone is complex enough, but you start stacking different symmetries on top of each other and having those all interact with each other, like, you're starting to get into some highly complex territory. And, you know, while I'm riffing on it, if there happens to be some base fundamental fabric of the universe that is, like, built using some kind of QC structure, and you have all these other emergent QC structures as you scale up from that Planckian scale or whatever, right? At the atomic level, it's a lot bigger than the Planckian. At the DNA level, it's a lot bigger than that. At the microtubule level, a lot bigger than that, right? At each of these emergent phenomena scales, maybe you're actually acting with different symmetries, and maybe there's some kind of upscaling or downscaling conversion of the information transfer from the lowest fabric of the universe up through the higher emergent levels, and then back down and back and forth. So maybe having differing symmetries like that could potentially be one way of communicating at different scales.
Okay, just taking notes. So, well, it's 4:41, guys. Should we wrap things up? It's been about going on close to 5 hours.
Yeah, I got to go set up a test for tomorrow.
Okay.
But
well, why not?
Tim, I noticed you're not wearing your Christmas hat.
Oh,
Like
you know what?
year.
It's it's buried. It is
It's
buried
dug
in the
mine out.
house.
So there we go. We're in the Christmas spirit.
Yeah, it is the Christmas spirit. I've been wrapping presents off and on. I've been doing it at a slow pace since Halloween. So
on that note, I'm printing quasi-crystal snowflakes right now as Christmas presents, just because I'm a little obsessed and it's the perfect gift for Christmas.
Are snowflakes quasi-crystals?
They can be, yeah. You can actually have quasi-crystalline snowflakes going on. Unfortunately, I can't stream the picture from the thing, but I can share a picture of what they look like here. Share screen. Come on,
Jared. Maybe if you put some quasi crystals on your rotaflyer thing, it'll take off.
See, you can have snowflakes that have the golden ratio in them, and quasi crystals.
You can stamp it into the pizza sheet or something.
Yeah.
There we go. See, there's a little Christmas spirit right there.
Yeah, buddy.
I love the Grinch.
You guys want to see it again? It's working really well.
Hit us, Harry. We can end on a propulsion note.
Okay, it's working really well right now. Watch how far it moves.
And I hope that thing is real. It's pretty sweet. Mechanical inertia transfer.
Is the thrust linear with the rotational velocity, or is there some other relationship?
Just don't see how you're getting past the atmospherics. Well, Merry Christmas. And to all a good night.
And a happy new year.
Yeah, that too.
Very happy.
Yeah, welcome to the group.
See here, Curtis, now. See, there's a little spirit, little Christmas spirit.
You started it, group.
All right.
Just like last year.
I had to dig it out. I didn't know. I had to ask the wife where it was. I haven't seen the stupid thing in a year. Which worries me, because that means we wasted a whole nother year on this madness. Okay, there we go. Got our little snowflake thing. That's nice. I don't even know what my system's doing. It's been spinning around for a while on its own.
You got to get that thing in the vacuum, Drew. Harry's thing.
I don't know. Key West is about an 8-hour drive from here. 9-hour drive.
Oh.
One user has a good one. They said, "Merry Apecmas."
You know, I'd be happy to throw that thing in there after I get done with my demos in January. But if it's truly mechanical flexure of the, well, first of all that wood, you'd take forever to pump that down. Oh, wait a minute. No, how deep do you got to go? A tour? Less than a tour?
Nope.
Couple of millitours?
You'd want to be less than a millitor for sure.
Oh, 10 to the -4?
Yeah.
Yeah.
Because you're just over the, I mean, especially if you're in a larger chamber, it might, I'd have to do the calc because you want to make sure the path length is a certain amount. For us, it's about that number for the 12, it's about 12-inch diameter chamber. For yours, it's probably a little bit higher.
It went about 90 degrees that time.
Yep.
Yeah, I'd be worried. I'm just, I don't know. I hope it's real.
It's also worth mentioning that this angular to linear momentum thing, in addition to the methods that have been discussed already, like it's already a technology that's up on satellites right now.
Yep.
That's the whole, like, you spin them up and it's two flat counter rotatings like this, and you swing them out really hard and fast, and they slow down, and then you slowly bring them back to their original position, and you speed them back up, and you do it again, and it's only like 1% efficient. It's super inefficient, but you don't really care about the efficiency because you got all the thrust you need to be able to at least do station keeping for your satellites, right?
Well,
Right.
and it's iterative too, right? And that's what I love about Harry's project is, not just Harry's, but like Drew is doing the same thing, and Curtis, you guys are doing the same thing. It's iterative, right? It's small incremental improvements. It's like once you start to see that result, you're able to build on that, narrow it in, refine it, and iterate on it. So that's amazing. So.
Oh, it's definitely an iterative process. I've taken
Yeah.
to where I change one thing at a time. And,
Yeah.
there's a lot of stuff to change. But if you change 2 things, you might as well change 50 things because you're never going to figure out what happened. It's definitely one stupid little thing at a time. So with that, gentlemen and ladies that might be out there.
Yeah. Well, guys, why don't we
holiday.
close things? Yeah, we'll close things down. Merry Christmas to everybody.
Yes,
Guys, thank you. I'm sorry for forgetting my Christmas hat, but and thank you to everybody for presenting. Harry, Steve, for lab updates, for Curtis, Drew, Jared, guys, Mikolaj, thank you. Thank all of you. It's amazing. Things are moving forward. We have seen so much forward movement this year. So all of these projects, this area is exploding. It's amazing. Okay, well, with that, this has been APEC for December 21st, 2024.
Merry Christmas, everybody.
Merry Christmas.
Merry Christmas.